Hello fellow sapiens, and welcome to Sleepless Homo. If you're here, it probably means your brain hasn't quite powered down yet, or maybe you're just looking for something a little quieter, whether you're lying in bed, drifting towards sleep, or just letting this play softly in the background while cooking, showering, or working with headphones on. This is your moment to slow down and wander backward. Not into fantasy, but into the deep past, into science, into memory. This is a channel for soft science, not wild speculation. Everything you'll hear is grounded in archaeology, paleontology, and humble evolutionary theory. We don't have all the answers, but we do have the bones, the rocks, and the questions. And if you ever drift off during one of the chapters, that's completely fine. I've left full timestamps in the description so you can pick up exactly where you left off tomorrow. Because this story, from the first second to the last, is worth hearing in full. Now, if you enjoy this kind of quiet, long-form storytelling, if it helps you learn, focus, or just relax after a loud day, consider liking and subscribing. It helps this channel reach more curious sapiens like you, and if you feel like sharing, tell us where or how you listen. Are you in bed, working a night shift in silence somewhere far away? And as always, stay curious, stay calm. Now, let's go back over 200 million years, to a world without flowers, without birds, without continents as we know them, a hot planet, a broken supercontinent, and the strange, unstoppable creatures who would come to rule it. This is the Jurassic Period, and this is the part we almost forgot. If you're still with me, then your mind is open and your day is softening. Let's go back. Not a few centuries, not a few million years, all the way back to a moment just after the world almost ended. The clock reads somewhere around 201 million years before today, though no clock ticks loud enough to hear it. There is no sky you would recognise, no Atlantic, no Himalayas. Just a heat-humming world built mostly from silence and steam. One supercontinent, one ocean, and one very recent extinction, because the Jurassic does not begin with life, it begins with death, or at least with the unmaking of what came before. At the very end of the Triassic period, in one of the 5 major mass extinctions of the Phanerozoic eon, nearly half of all marine species vanished. Entire ecological networks gone. In the seas, once thriving families of mollusks and corals disappeared. On land, many of the dominant archosaurs collapsed into silence. It wasn't the largest extinction in Earth's history, but it was precise and oddly timed, and like most things from that far back, still not fully understood. Volcanic activity from the Central Atlantic magmatic province is one of the most likely suspects. It's hard to ignore a lava field that once stretched from what is now Brazil to what is now France. Imagine 4 million square kilometres of fissures and basalt flows, releasing more carbon dioxide than we can reasonably imagine. The air filled with it. The oceans warmed, the carbon cycle snapped, and then nothing. For a while. But this is where the story turns, because for all the horror implied in an extinction event, there is a strange kind of creative potential that follows. When ecosystems collapse, niches open. When dominant species vanish, new ones try to crawl into the space left behind. And when the entire world has just been shocked into silence, even small survivors can get loud. So begins the Jurassic. Not with an explosion, but with a slow reclaiming. The air is thick, the poles are warm, the continents are starting to tear away from each other like tired puzzle pieces whose edges no longer fit. And across this trembling crust, life begins to surge back, stronger, stranger, and far more ambitious than before. At the start of the Jurassic, the face of the Earth looked simple, almost too simple. One giant supercontinent Pangaea, still loosely stitched together, stretched from pole to pole like an ancient crustal monolith. But beneath it, the engine of plate tectonics was churning. Subduction zones deepened, mantle plumes pushed upward. The great unbreaking had already begun. By around 200 million years ago, fissures and rift valleys began to open across what is now the Central Atlantic margin. Lava poured upward in immense pulses, releasing sulfur and carbon dioxide into the sky in alternating waves. That tectonic violence, seismic and slow, would gradually rip Pangaea into two main daughter continents, Laurasia to the north and Gondwana to the south. Between them, narrow basins filled with seawater, marking the birth of the Atlantic Ocean, though it was more like a trickle than a flood. These weren't clean continental splits. The tectonic plates didn't slide away from each other like drawers. They cracked and pulled and jammed, breaking in different places at different speeds. As Laurasia and Gondwana drifted apart, shallow epicontinental seas began creeping into low-lying areas. What had once been a single landmass was slowly reshaped into a broken archipelago of continental fragments. Regions that today sit thousands of kilometres apart were still shoulder to shoulder, South America almost kissing Africa, Antarctica nestled into Australia like the last spoons in a drawer. The Gulf of Mexico began to open. The North Sea basin was just a depression in the middle of the continent. The geography of the modern world hadn't formed yet, but its tectonic instructions were already printing in basalt and fault lines, and above all of this movement, the climate. If you've ever wondered what a high CO2 world feels like, the early Jurassic might be your best laboratory. Atmospheric carbon dioxide levels were likely 4 to 5 times higher than pre-industrial modern Earth. Global temperatures were as much as 5 to 10 degrees Celsius warmer. There were no permanent polar ice caps. Rainfall patterns, fed by increased ocean evaporation, likely created belts of intense humidity near the equator, and more temperate but still wet conditions in mid-latitudes. The seasons were muted, the tropics were vast, and most of the Earth, especially in the early stages, was blanketed not in deserts, but in dense, steamy forests and fern-slick swamps. This wasn't a planet of extremes. It was in many ways eerily comfortable. Not too hot, not too cold, just unrelenting. The kind of climate where evolution doesn't need to pause for winter. The kind where you don't freeze to death at night. A world with more steam than storm. And that consistency, strange as it sounds, may have been one of the key drivers of the Jurassic explosion in biodiversity that would follow. Because when climates are stable for long enough, life gets experimental, but stability is never simple. The volcanic activity that helped cause the end Triassic extinction did not stop at the boundary line. Throughout the early Jurassic, massive basalt flows continued to erupt in pulses across what is now Western Europe, North Africa, and Eastern North America. These were not isolated events. They were episodic, continent-scale exhalations of the deep Earth. And with each one came new gases, new minerals, and a new atmospheric rebalancing act. Some scientists proposed that the early Jurassic greenhouse was not constant but punctuated, fluctuating between brief cooling intervals and longer periods of warmth. Ocean anoxia events may have occurred sporadically as well, suffocating marine life and trapping more carbon in deep sediments. The carbon cycle of the early Jurassic was a system running on the edge, driven by volcanism, mediated by ocean chemistry, and altered by the slow emergence of vast swampy plant cover that would later become coal. We often imagine ancient worlds as more alien than they truly were. But the early Jurassic wasn't a fantasy realm. It was familiar in its chaos. A world of slow disasters and fast recoveries. A world learning to rebalance itself after trauma. And like any recovering world, it left behind clues. Chemical whispers in rocks, isotopic ratios in ancient marine shells, patterns in zircon crystal cooling, shifts in carbon isotope values across boundary layers. We can't time travel, but the rocks remember. At sites like the Blue Lias Formation in southern England or the Ferny Shale of western Canada, thin, dark layers rich in organic carbon tell us of sudden disoxycotions. In the Tethyan realm, now a fossilised belt through southern Europe and North Africa, we find sedimentation patterns that mark changes in sea level and tectonic tilt. All of these speak to a planet in motion, not just across space, but through cycles of atmospheric, biological and chemical change, and perhaps most haunting of all. For a brief moment, Earth's geography and climate aligned to allow life to spread almost without interruption. The breakup of Pangaea had created both new barriers and new corridors. Inland seas allowed for aquatic expansion. Shifting coastlines created isolated zones where new evolutionary experiments could incubate. Even the magnetic field, stronger in the Jurassic than it is now, may have helped shield life from damaging radiation during this critical phase of recovery. For tens of millions of years, Earth was, in a strange way, unusually kind to the organisms that survived the last extinction. Not peaceful, not stable, but survivable, expandable, and oddly fertile. But no matter how stable a world may seem, it doesn't last. The Jurassic would go on to host some of the most famous organisms in the history of life on Earth. But right now, at its beginning, it is still quiet, still under construction. The continents are drifting, the skies are heavy, the seas are rising, the stage is being set. And if you lean in close enough, you might just hear the low rumble of something ancient, something rising from the ash and soot, ready to reclaim the Earth in forms we've never fully understood. So we end this moment not with a creature, but with a question. If life can rebound after an extinction this massive, how many other times has it tried, and how many times have we simply forgotten? If you stepped outside 190 million years ago, you wouldn't need a jacket, or an ice scraper, or a weather forecast, because in the Jurassic world the weather didn't really change, not the way we think of it. No snowstorms at the poles, no annual frost lines, no long dry winters or long wet summers, just a kind of steady, wet warmth, unrelenting, humid, and oddly livable. A greenhouse world, breathing slow through volcanoes and jungles, cycling carbon through rocks and oceans, mist and rainfall, all without ever dipping below freezing. There were no glaciers, no ice caps, no seasonal snowfall that lasted. In fact, for tens of millions of years, Earth may have forgotten how to make ice entirely. But how? How does a planet run that hot, that stable for that long? And how does anything survive in the process? To understand Jurassic life, you have to understand Jurassic air. Not what you breathe, but what shapes the rhythms of survival. And it begins, always, with carbon. Carbon dioxide, that tiny molecular thread running through volcanism, photosynthesis, decay, and deep burial, is not just a greenhouse gas. It's one of the planet's oldest climate levers. During the early to middle Jurassic, atmospheric CO2 levels may have hovered between 1,000 and 3,000 parts per million, roughly 4 to 10 times higher than pre-industrial Earth. It's hard to be exact. No air samples remain, but we can read its echoes in fossilized plant stomata, in the isotopic ratios of paleosols, and in the carbon signatures left behind in marine carbonate deposits. And what all those signs point to is a planet in greenhouse overdrive. Higher CO2 concentrations don't just trap heat, they change everything. Ocean surface temperatures rise, the difference between equator and pole shrinks, Hadley cells, the great convective currents that move air and moisture from the tropics toward the mid-latitudes expand their reach. The hydrological cycle spins up, more evaporation from the seas, more cloud formation, more rain, less contrast, a quieter kind of chaos. But here's where it gets strange. Despite the heat, and despite the rain, the Jurassic atmosphere wasn't suffocating. At least not for the life that evolved within it. CO2 wasn't a pollutant, it was a background condition, an invisible architect of forests, swamps, and oxygen-producing giants. In fact, during the Jurassic, atmospheric oxygen levels may have also been slightly elevated compared to modern Earth. Not dramatically, perhaps around 25%, but enough to feed larger metabolic systems, fuel faster movement, and support organisms that, in today's thinner balance, might struggle to grow at all. That balance of CO2 and O2 was not fixed. It fluctuated across millions of years, but during the core of the Jurassic it allowed ecosystems to stretch into forms we don't fully see anymore. Not because the air was magical, but because it was consistent. That consistency wasn't an accident. It was the result of a long and unstable equilibrium between the inputs and outputs of the carbon cycle. Volcanic activity injected massive amounts of carbon dioxide into the atmosphere, especially during the breakup of Pangaea and the formation of new ocean basins. But over time, that CO2 didn't stay in the sky. It was absorbed by weathering rocks, pulled into soils, consumed by photosynthetic plants, and eventually buried in sediments that would one day become chalk, shale, or coal. This balance of source and sink is what makes Earth different from Venus. It's what kept Jurassic Earth habitable, even with no ice caps and no polar snow. The thermostat wasn't broken, it was just set differently. And while CO2 drove the heat, It was water vapour that sealed the deal. The Jurassic was not just a carbon-rich world, it was a humid one. With more evaporation came more clouds, and with more clouds came a strange kind of thermal feedback. High-altitude clouds reflected sunlight, keeping the surface slightly cooler during the day. Low-altitude clouds trapped infrared radiation, keeping the nights unnaturally warm. The result was a world with less daily temperature variation, less seasonal fluctuation, and far more atmospheric stability than we might expect from a high CO2 planet. In the tropics, rainfall may have been near constant. In the mid-latitudes, seasonal monsoons likely surged and retreated like biological tides, feeding vast wetland belts. At the poles, temperatures may have remained warm enough to sustain forests, not the boreal conifers of today, but swampy, fern-covered ecosystems that knew no frost. This climate engine, spinning quietly behind the scenes, didn't just shape temperature, it reshaped biology. In a world without winter, organisms don't need hibernation. They don't need antifreeze proteins. They don't build thick fur coats or store food for a season that never comes. Instead, they evolve into forms suited for constancy, slow-growing, long-limbed, with year-round reproductive cycles and no need to pause for snow. The very idea of a cold-blooded creature becomes blurry in a world where the environment stays warm 24 hours a day. Ectotherms thrive, endotherms spread, and every niche, from swamp floor to canopy to shallow bay, becomes an evolutionary arena running at full speed. Of course, not every part of the Jurassic world was equally tropical. There were still temperature gradients, still dry zones and floodplains, still arid uplands and wind-swept coastal shelves. But the overall range of habitable environments was far broader than today. Polar regions may have been temperate enough to support amphibians. Mid-latitude belts likely supported dense forests with minimal seasonal dieback. And in the equatorial zones, vast floodplains may have stretched uninterrupted for hundreds of kilometres. It wasn't paradise. It was just warm enough and wet enough for life to get busy, and that busyness came with consequences. More vegetation meant more carbon drawdown, especially in swampy, low-oxygen environments where plant matter could be buried rather than fully decomposed. This is part of why Jurassic coal seams exist, even in a greenhouse world. In some intervals, photosynthetic drawdown may have outpaced volcanic input, leading to brief periods of cooling, or at least climate moderation. The Earth didn't just sit there, it breathed, in and out, warm, wetter, warmer, wetter still, sometimes cooling, sometimes stormier, but always cycling, always slow. This rhythm wasn't just driven by gases. Orbital cycles played their part too. The Earth's axial tilt, orbital eccentricity and precession all affected the distribution of sunlight and the timing of seasons, even in a greenhouse world. These Milankovitch cycles, still active today, would have produced subtle variations in monsoon strength, sediment deposition, and biological productivity over spans of 20,000, 40,000, and 100,000 years. In the rock record, we see this as varves, fine, alternating bands of silt and clay that preserve seasonal or annual patterns. In some Jurassic formations, these microlayers stretch uninterrupted for tens of meters, telling us not just that the world was stable, but that it pulsed, pulsing, breathing, but not pausing. Because when the Earth runs warm for long enough, the biosphere doesn't just recover, it explodes. Still, for all its warmth, this was not a greenhouse of comfort. Storms in the Jurassic were likely intense. Tropical cyclones, unbroken by modern land masses, may have swept across shallow seas with unimaginable energy. Lightning storms could have stretched for days, and rainfall, measured not in inches but in meters, may have reshaped entire floodplains in a single week. The soil beneath your feet would never fully dry. The air would always carry the weight of water, and the sky would never stay the same shade of blue for long. And yet, something in that chaos worked. The air was breathable, the land was fertile, the seas were warm, oxygen supported life, carbon dioxide drove growth, and clouds, those quiet agents of both cooling and trapping, regulated the planet like a second skin. It was not balance, it was dynamic imbalance. A planet not frozen in stasis but held together by cycles we are only beginning to understand. So if you're wondering how life survived when the thermostat was broken, maybe it wasn't broken after all. Maybe the Jurassic world wasn't a mistake. Maybe it was just another version of normal. And the real question is, how many other versions have we already forgotten? There was a time when Earth's map was nearly blank. Not in the sense of lacking detail, but in the sense that there were no coastlines, no tangled archipelagos or open ocean trenches, just one sprawling supercontinent called Pangaea, surrounded by a single global ocean. It was a landmass so massive that it created its own weather, so fused together that its interior likely baked under seasonal extremes, far from the stabilising influence of the sea. But this simplicity wouldn't last. For reasons still not entirely clear, something began to shift beneath the crust, and over the next tens of millions of years, the very floor beneath ancient life began to fracture. Land didn't just move, it broke, and in the cracks between those broken pieces, new oceans began to form. We tend to think of continents as permanent features, fixed theatres for the drama of evolution, but they're more like temporary rafts of crust, floating on a deeper, hotter, moving engine. And by the earliest days of the Jurassic, that engine was beginning to tear Pangaea apart. The first hints likely came as rift valleys, long depressions in the continental crust where tectonic plates begin to pull away from each other. These valleys often flood, sink, and widen over time, marking the early stages of ocean birth. Around 200 million years ago, these rift zones began to spider outward across the land, tracing future fault lines between what would one day become North America, Europe, Africa, and beyond. The most iconic tear would become the North Atlantic. At the dawn of the Jurassic, it was only a suggestion, a series of inland basins and rifting faults snaking between what we now call eastern North America and northwestern Africa. But over the next 30 million years, those basins widened. Lava bled through the cracks. Massive outpourings of magma formed what geologists now refer to as the Central Atlantic Magmatic Province, a planetary-scale volcanic event that may have helped trigger the extinction at the end of the Triassic. But by the early Jurassic, the worst had passed and the rift zones remained active. Slowly, relentlessly, the land drifted apart. As the faults widened, seawater poured in. Inland valleys became shallow seas. The North Atlantic, still narrow and immature, was born from these flooded fractures. To the south, Gondwana, and the southern half of the supercontinent, began to fracture as well. Antarctica, Australia, South America, Africa, and the Indian subcontinent were still welded together, but strain lines had begun to form. These were not yet oceans, not even seas. But the land was growing restless. The eastern part of Gondwana began pulling away from the western edge, setting in motion a future that would eventually open the South Atlantic and reshape the Indian Ocean. In between these vast continental masses, shallow seaways began to pulse with warm currents. These proto-oceans would become vital for life. They didn't just divide continents, they connected ecosystems. For the first time in hundreds of millions of years, marine corridors opened up between isolated regions, offering passage to species that would otherwise have remained landlocked or regionally trapped. In what is now Europe, the tectonic reshaping led to the formation of several key basins. The Germanic Basin, the Anglo-Paris Basin, and the Western Siberian Basin all owe their origins to this slow continental wrenching. These weren't oceans, but they were large enough to hold vast epicontinental seas, shallow bodies of salt water that periodically flooded the land. With no polar ice caps and a globally warm climate, sea levels were high, and when crustal downwarping met rising water, the result was a patchwork of inland seas, coastal lagoons, and flooded plains. Further north, in what we would now call Eurasia, a similar story was playing out. Tectonic stretching in the region that would become the Arctic Ocean caused marine waters to flood parts of the northern landmass. These new seaways linked to deeper bodies and provided nutrient-rich corridors where marine reptiles, ammonites, and future evolutionary branches would begin to flourish. The Arctic coastlines were not frozen wastelands. They were lush, temperate shorelines, flooded and fertile. Volcanism followed the fractures. As the continents drifted, magma surged upward along the rift zones. The Earth's crust, thinned by extension, allowed enormous volcanic flows to blanket the landscape. These weren't tidy volcanoes like we see in modern times. These were massive flood basalts, liquid rock pouring out of the planet in sheets that could bury regions the size of modern countries. The surface of the Earth, in places, was red hot and glowing. And while these events were less apocalyptic than the ones that marked the end of the Triassic, they still had profound environmental consequences. They added heat to an already warm planet, they pumped carbon dioxide into the air, and they reshaped the land into a kind of tectonic mosaic, with newly formed ridges, faults, and ocean floors slowly sculpting the world we know today. Beneath the oceans, a new kind of crust was being formed, mid-ocean ridges. These underwater mountain ranges marked the boundaries where new seafloor was born. As magma rose and solidified, it pushed older crust outward, driving the continents further apart. The Atlantic Ocean as we know it was still narrow, but its engine had started. The Mid-Atlantic Ridge, now one of the longest mountain chains on Earth, had its roots in these Jurassic beginnings. With each pulse of volcanic activity, more basaltic crust was added, and with each addition, the ocean widened, inch by inch, year by year, continent by continent. What's often forgotten is that this entire planetary reshaping happened quietly, not in a single moment of dramatic catastrophe, but through cumulative shifts over tens of millions of years. If you were alive during the early Jurassic, say, around 190 million years ago, the world might have looked largely stable to your eyes. The mountains would still be where they were last season. The coastline might seem familiar, but over deep time, the familiar was always temporary. Valleys deepened, faults widened, seas rose, and the slow rupture of the world beneath your feet continued. By the Middle Jurassic, around 170 million years ago, the map had changed. The Atlantic Ocean was narrow but real. The Tethys Ocean, once a vast inland sea between Gondwana and Laurasia, had expanded and connected to new marine pathways. India was beginning to drift northward. Australia and Antarctica remained fused, but subtle fault lines hinted at future separation. The supercontinent was gone, in spirit if not yet in full geography. In its place was a planet in motion, a planet cracking, a planet rearranging itself from a single landmass into the beginnings of a global puzzle. What this meant for life would unfold in later eras, but tectonics had done something strange and powerful. By tearing the land apart, it had created opportunity. Isolation led to speciation. Flooded basins became nurseries for marine life. Mountain ranges altered wind and rainfall patterns, and perhaps most importantly, the vast connected coastlines provided countless ecological edges, the transitional zones where evolutionary creativity tends to spike. So when we ask why the Jurassic became such a fertile, diverse and strange era in Earth's history, we must not only look to its creatures or its climate, we must look beneath it, to the quiet, inexorable breakage of land. The crust itself had shifted, the world had been cracked open, and in those cracks life would soon take hold with astonishing force. But this also leaves us with a strange, haunting question. If the continents had never fractured, if the plates had never pulled away from each other, would life have diversified at all? Would there have been enough separation, enough movement, enough boundary and edge to spark the evolutionary fireworks of the future? Or was it the rupture, not the unity, that truly made our world alive? That's the part we're still trying to understand, and perhaps always will be. What did forests look like before petals evolved? It's a simple enough question, but behind it lies a world that almost doesn't make sense to the modern eye. No blossoms, no bees, no splash of springtime pink, just towering green, textures instead of colours, spores instead of sweetness, and a slow-motion ecological ballet choreographed not by scent or nectar, but by wind and patience. This was the Jurassic Forest. From roughly 200 million to 160 million years ago, Earth was a greenhouse world without flowers. It was hot, wet, and deeply green, and the plants that ruled it were neither delicate nor shy. They were survivors of the extinction that had cleared the board at the end of the Triassic, and they wasted no time reclaiming the space left behind. Within just a few million years of the chaos, plant life had erupted across the continents, in a chlorophyll conquest that turned even rocky slopes and rift basins into jungles. But not the kind of jungle you're picturing. There were no orchids, no grass, no tangled underbrush as we know it. Instead, Jurassic forests were structured like botanical cathedrals, airy fern-floored halls held aloft by giant seed plants that had been evolving since the Carboniferous. These were ecosystems of slow innovation, built entirely on gymnosperms. The term gymnosperm simply means naked seed. Unlike flowering plants, which protect their seeds inside fruits, gymnosperms expose theirs on scales or cones. This group includes conifers, cycads, ginkgos, and several now extinct lineages. And in the Jurassic, they were not only dominant, they were foundational. The vast majority of terrestrial biomass came from their trunks, leaves, and roots. And the ecosystems they built provided the structural and climatic backdrop for the dinosaurs' evolutionary explosion. Among the first to re-establish themselves after the Triassic-Jurassic extinction were the cycads. Often mistaken for palms today, cycads are actually more ancient and genetically distinct. They have thick, armoured trunks crowned with rosettes of stiff, feathery leaves. In the Jurassic, they flourished across the tropics and subtropics, forming dense, low forests in coastal plains and flood basins. Their seeds were large, often toxic, and may have been among the earliest plant foods sought out, or avoided, by herbivorous dinosaurs. Cycads are dioecious, meaning male and female cones grow on separate plants. Their reproductive strategy involved cones packed with exposed ovules and pollen released into the wind. Yet even with this seemingly simple setup, some Jurassic cycads evolved elaborate cone shapes, possibly as a form of thermogenesis or even rudimentary signalling, not for insects, but perhaps for wind optimization. We don't know for certain, we only have the cones, and a few fossilized impressions of their leaves, pressed like green memories into stone. Above the cycads rose the conifers. Today we associate conifers with cold northern forests, pine, spruce, and fir. But in the Jurassic they thrived in warm, humid zones as well. Their diversity was immense, and many belong to extinct families that have no true modern analogues. One example is the genus Podosomites, which once dominated the mid-latitudes of East Asia. Unlike modern conifers, Podosomites had broad, flat leaves that looked more like magnolia foliage than needles, and it was deciduous. These were conifers that shed their leaves seasonally, adapting not to winter frost, but perhaps to dry spells or other stressors. Some grew in swampy lowlands, others lined upland river valleys, and all of them fed the fire cycle of the Jurassic, not just metaphorically, but literally. Their resinous wood and dry needle litter made wildfires a common feature of this ancient world, though perhaps less intense than today due to the higher oxygen levels and widespread humidity. In parts of what is now Europe, especially the Germanic Basin and the British Isles, we find evidence of another conifer-dominated flora. The group Caerulepidiaceae, now entirely extinct, was a defining feature of many Jurassic environments. These trees had thick, scaly leaves and a high tolerance for salty or nutrient-poor soils. Some even adapted to coastal or semi-arid habitats, where they may have played a role in stabilising sand dunes or resisting brackish flooding. Their fossils show strange leaf and cone morphologies, hinting at ecological strategies no longer seen today. And then there were the ginkgos. If you've ever walked a city street lined with fan-leaved ginkgo trees, you've seen a ghost. Ginkgo biloba, the only surviving species of a once diverse lineage, is a Jurassic relic. But in its heyday, the ginkgo family spread across much of Laurasia, particularly in temperate regions. Fossil records from China, Mongolia and Central Asia show multiple genera of ginkgo-like plants, some with lobed leaves, others with more complex venation patterns. Their seeds were exposed on stalks, not enclosed in cones, and may have been dispersed by wind or gravity alone. Ginkgo wood is relatively soft, and its growth rings suggest a seasonal rhythm, possibly influenced by monsoon cycles. In forested valleys of the early Middle Jurassic, ginkgos formed open canopy groves that mingled with conifers and ferns, creating a layered ecosystem of tall trunks, mid-level shrubs, and mossy fern-covered understory. Seed ferns, already ancient by this point, were in their twilight, but they still held on in some regions. These were not true ferns, but rather plants with fern-like leaves and seed-based reproduction. Their lineage stretches back to the late Paleozoic, and by the Jurassic they had evolved into strange woody shrubs with thick leaf fronds and complex root systems. In some places they formed underbrush beneath taller cycads and conifers. In others, they clung to rocky slopes or lake margins, stabilising soil and supporting early terrestrial ecosystems in ways that are easy to overlook but ecologically vital. Their extinction toward the end of the Jurassic was gradual but definitive, and today only their impressions remain. One of the most important things to understand about these Jurassic forests is not just their composition, but their verticality. These were tall, stratified ecosystems. Some conifers may have reached over 30 metres in height, with lateral branches creating shaded canopies that regulated temperature and humidity beneath. The forest floor, depending on region, could be open and fern-covered, or tangled with juvenile gymnosperms and moss. In riparian zones, where rivers cut through the floodplains, vegetation may have been more diverse, with a mix of swamp-dwelling trees and seasonal herbaceous cover. But across all these environments, the absence of flowering plants meant that colours were muted. Greens and browns, occasional reds from cone scales, maybe hints of silver on leaf undersides, but nothing like the pollinator-driven palette of the Cretaceous and beyond. Photosynthetic efficiency was high, especially in the equatorial and mid-latitude zones where sunlight was abundant. But the CO2-rich atmosphere and the warmth of the period also meant plants grew rapidly. Growth rings in fossil wood show fast seasonal expansion, followed by quick dormancy. This suggests that despite the generally warm climate, many Jurassic regions still experience some form of seasonality, likely driven more by rainfall than temperature. Wet and dry seasons, not summer and winter, and the plants evolved accordingly. We also find evidence of root systems that hint at soil stabilisation strategies. Fossilised root casts show networks that mirror modern forests in function, if not in form. These roots not only anchored the trees but shaped the very land they grew on, slowing erosion, filtering water, and creating microhabitats for whatever animals and microbes had made their homes in the understory. In some deposits, especially in China's Yunnan region and parts of Patagonia, paleobotanists have uncovered entire fossilised forests, where fallen trunks, leaf litter, and even root mats are preserved in situ. These snapshots give us rare three-dimensional glimpses into the Jurassic world. They show trees spaced unevenly, with clearings and dense patches, and sometimes signs of fire damage followed by regrowth. These are forests that lived and died and returned, over and over, in a cycle older than any species that would later walk through them. Today, only a handful of these Jurassic giants remain. The cycads are still here, clinging to subtropical zones. The ginkgo, kept alive by humans in urban landscapes and temple gardens. A few conifers, distant cousins of their ancient relatives, still dominate boreal forests. But most of the Jurassic flora is gone, not dramatically, not all at once, just slowly outcompeted, mutated or rendered obsolete by the flowering plants that eventually rose to take their place. And so, we're left with a question. One that science can't fully answer, and maybe never will. What does a world smell like before flowers? What does a breeze carry when there is no perfume, no petal, no fruit? Perhaps just the scent of resin and spores, the whisper of wind through fern fronds, and the quiet, steady breath of a forest that had not yet learned to bloom, but had already mastered the art of life. You already know the stereotype, that insects and flowers go together, that bees and blossoms are the original love story. But the Earth did not start that way. The Jurassic forests were thick with life, but not with colour. There were no petals yet, no roses, no fruit, and no bees. So how then did it work? Who spread the pollen? Who landed on the cones? Who exactly flirted with the trees before flowers ever thought to bloom? It turns out that even in a world without petals, the dance between plant and insect had already begun. Just not the way you'd expect. For nearly 50 million years, the Earth hosted a strange courtship, a silent pre-floral ecology, where the first pollinators learned to visit the forest's reproductive organs without knowing they were rehearsing for a future that hadn't evolved yet. Let's step into that world, back to a time between 190 and 150 million years ago, the middle of the Jurassic, a planet without petals, but not without pollinators. By this time, the forests had already become layered, complex systems. There were ginkgos with fan-shaped leaves, cycads with thick trunks and pineapple-sized cones, and towering conifers with pollen sacs at their tips, and resin in their bark. The air was warm, the atmosphere thick with carbon dioxide, and in many places the undergrowth steamed like a greenhouse. But the real story, the one hiding in the shadows of the leaves, was what crawled, buzzed, and fluttered between these plants, and how these tiny animals began to rewrite the rules of reproduction. The Jurassic insect world was not a primitive sideshow, it was a world of innovation. Across East Asia, in what is now northeastern China, a fossil-rich region called the Daohugu Beds preserves some of the best glimpses we have of this time. Trapped in volcanic ash and fine lake sediments, dozens of ancient insect lineages reveal a story stranger than expected. There were early beetles, small and low to the ground, that chewed through decaying vegetation and possibly burrowed inside ancient cones. There were wasp-like insects with ovipositors longer than their own bodies. There were moth-like forms with scaly wings, but no modern flowers to land on. And then there were the butterflies that weren't. Enter the calligramatids, often called calti for short. If you looked at one hovering above the Jurassic ferns, your modern brain might mistake it for a butterfly. Broad, patterned wings, a long tongue-like proboscis, a gentle flight through the sunbeams of the forest canopy. But calligramatids weren't butterflies at all. They belonged to an entirely different order of insects, closer in ancestry to lacewings than to anything lepidopteran. In other words, evolution had built something butterfly-like from entirely different materials, and that, right there, is where the story becomes deeply human. Because what we're seeing here isn't just mimicry, it's convergent evolution, a pattern repeated not because of ancestry but because of shared ecological pressures. These Jurassic calti evolved long tongues not to drink nectar from flowers, but likely to access sugary fluids secreted by gymnosperm cones, structures that, while very different from petals, still needed to lure in animals to move their pollen around. Some of these cones had elongated necks or tubular forms, mimicking the basic geometry that future flowers would perfect. It was a different stage, a different cast. But the choreography had already begun. We don't know exactly how widespread this pre-flower pollination was. The fossil record is partial, scattered, and more generous in some sediments than others. But what we do know is that insects like calligramatids were common and morphologically well suited for plant interaction. Their mouthparts were specialised, their wing structures adapted for hovering flight, and their fossilised gut contents sometimes even preserved plant matter, hinting at a mutualism far older than the angiosperms that would later dominate the Earth. They weren't alone. Some beetle lineages, particularly early Polyphaga, were already thriving in Jurassic forests. These beetles were the recyclers, the first decomposers, crawling through leaf litter, feeding on fungal spores, and occasionally climbing conifer branches to nibble on soft pollen structures. While it's hard to say how intentional their pollen transport was, some may have served as accidental vectors for reproduction, clumsy, chewing pollinators long before the elegance of bees arrived. But perhaps the most poetic irony is that most of these creatures vanished before the flowers ever came. By the early Cretaceous, as angiosperms exploded across the continents, many Jurassic insect groups declined. The calligramatids, once so dominant and diverse, went extinct. Their butterfly-shaped wings would be found only in stone. Their proboscises would be fossilised in ancient lake beds, while real butterflies, true lepidopterans, began to evolve on a separate path. It's almost as if nature rehearsed the performance with one cast, only to replace them all before opening night. Still, their contribution remains. They proved that even without petals, attraction could evolve. The eye spots, wing patterns, and chemical signals could exist without flowers to demand them. That the relationship between plant and insect was not born in the bright spring of the Cretaceous, but in the dim, fern-choked understories of the Jurassic. There's something deeply grounding in that. We tend to imagine evolution as a march toward complexity, as if butterflies required flowers, as if bees needed nectar, as if everything is tied up in the relationships we already know. But life doesn't care about our categories. Life finds overlap. Life experiments. Life rehearses roles before it writes the final play. And this raises a haunting question. How many other almosts have there been? How many strange mutualisms bloomed and vanished before leaving a trace? How many insects visited cones under a Jurassic sun, unknowingly preparing for a world that would never quite include them? When we find a fossil of a caltiwing, perfectly preserved in Chinese shale, we're not just looking at a dead insect, we're looking at a failed future, a draft of something that almost made it. And yet, in that failure, there's brilliance, because nature was already thinking like a pollinator, already designing tongues, already inventing camouflage, mimicry, and co-evolution, millions of years before petals ever opened. So the next time you see a bee land on a flower, remember that they were not the first, just the latest. The Jurassic forests were already humming, already buzzing, already reaching out to the air, hoping that something, anything, would land, taste, and carry their story forward. And something did. They were never invited to the spotlight, not when forests towered above them, not when shadows lengthened under the feet of giants, not even when they first scurried, silent and soft under the ferns that nobody remembers. But the story of the Jurassic is not only about reptiles with necks like cranes or teeth like saw blades. There were others, smaller, stranger, furrier, and still here, somehow. When we picture the Jurassic world, it is tempting to think only in terms of the enormous. But what if we zoomed in? What if we lowered our perspective not to the branches of conifers or the bones of sauropods, but to the roots? Beneath the leaf litter, behind rocks, under logs half-eaten by fungi, life continued in miniature. And in those hidden corners, evolution quietly rehearsed the mammalian experiment, an idea that would not truly take over the Earth for another 100 million years, but which began not in triumph, but in survival. By the start of the Jurassic Period, around 200 million years ago, the extinction at the end of the Triassic had reset much of Earth's biological order. Dinosaurs began their rise to dominance, and reptiles flourished in niches across land, sea, and air. But the early mammals, they stayed low, literally, and in doing so, they may have found the one evolutionary strategy that could coexist with thunderous feet and sharp-toothed cousins, be small, be nocturnal, be quiet, and be everywhere. Multituberculates are often considered the rodent analogues of the Mesozoic world, though technically they are not rodents, and technically, rodents would not show up for another 130 million years, but analogies help. If you imagine a creature roughly the size of a modern rat or guinea pig, with gnawing teeth and a flexible body built for climbing or burrowing, you would not be far off. They were called multituberculates because of their complex, multicusped teeth, rows of little bumps and ridges, perfectly evolved for chewing through plant matter, seeds, and maybe even insects. The group would persist for over 100 million years, a tenure far longer than most dinosaur families, and yet their names remain unknown to most. Fossils like Pulchophatia or Queniotherium do not make it into children's books, but they deserve to. Because the secret to their success was adaptability. Some multituberculates climbed trees, others burrowed underground, some had grasping paws. A few even developed gliding membranes, independently inventing the idea of the flying squirrel long before squirrels themselves evolved. They were evolutionary generalists in a world increasingly ruled by specialists. If multituberculates are the quiet heroes of mammalian history, then the docodonts are its forgotten philosophers, weirder, more eclectic, and with a surprisingly rich fossil record in China and Europe. The genus Docodon, first described from Jurassic sediments in what is now Germany, shows a dental pattern so sophisticated that it rivals some modern mammals. Their molars were complex, and complexity in the fossil record is rarely accidental. One of the most beautiful examples of Jurassic mammal evolution comes from the Middle Jurassic strata of northeastern China, where an animal known as Castrocauda, meaning beaver tail, made headlines not just for its anatomy, but for what it told us about mammalian experimentation. Castrocauda had a flat paddle-like tail, webbed feet, and evidence of fur. It likely lived in freshwater environments, swimming for prey. This is astonishing because it means that, while dinosaurs were stomping on land and pterosaurs were gliding above, at least one mammalian lineage had already re-entered the water, not to dominate it, not yet, but to live in it, quietly, successfully, and with style. Then there's Docker fossa, also from China, whose anatomy resembles that of a modern mole. Fossils show short, broad digits and a skeletal structure ideal for digging. Once again, this suggests convergent evolution, the independent invention of similar traits in unrelated animals due to similar ecological pressures. Moles evolved it later. Docker fossa got there first. This means Jurassic mammals were not just hiding, they were diversifying. And if the multituberculates were the generalists and the docodonts were the innovators, the therians were the ancestors, the ones who would eventually give rise to nearly every mammal alive today, including you. The earliest known therian is a small mouse-sized fossil named Juramaya, found in 160-million-year-old deposits in Liaoning Province, China. Its name means Jurassic Mother, and the name is not poetic. It may be quite literal. Juramaya appears to be one of the earliest relatives of placental mammals, the group that would eventually include primates, elephants, whales, and humans. This tiny creature had teeth for an insectivorous diet, long fingers for climbing, and a skeletal structure remarkably advanced for its age. It could grasp, it could climb, and it had traits in its ear bones and jaw that mark it clearly as part of the lineage that leads to us. And yet, it was less than 10 centimetres long, a whisper on the evolutionary stage. So what were these mammals doing, day to day, in a world dominated by reptilian behemoths? The answer, perhaps, is simply living. Some foraged in the leaf litter, feeding on worms or roots. Others gnawed at seeds or stalks. Many stayed nocturnal, not just for ecological advantage, but because of necessity, staying out of the way of larger, sharper eyes. Their vision likely adapted to low light. Their hearing, already improving with the transformation of jaw bones into ear bones, became acute. Smell played a central role, and the brain, slowly, quietly, it was getting bigger. One of the enduring mysteries of mammalian evolution is why, despite living in such constrained niches, the ancestors of modern mammals began to develop increasingly complex nervous systems. Why invest so much biological energy into cognition, coordination, and sensory integration if your entire job is to not be eaten? Perhaps the answer is that complexity is not always a response to dominance. Sometimes it's a response to navigating the margins. In a world full of danger, subtlety is a superpower. There is no evidence that Jurassic mammals hunted in packs or built elaborate social systems. They were not yet painting on cave walls or taming fire, but they were learning, adapting, evolving under pressure. The fossil record shows increasing variety in skull shapes, tooth arrangements, limb proportions. Each adaptation, each tiny shift in form, was a data point in the grand experiment of life. And though we know only fragments of their bones, what we do see is remarkable for its range. And so the story of Jurassic mammals is not one of dominance or grandeur. It is not cinematic. It is granular, compressed into crevices, preserved in the fine sediments of ancient lake beds. It is a story of survival by subtraction, of reducing visibility, lowering metabolic demands, staying light, fast, hidden. And in that quietness, they won. Not quickly, but permanently. Because every large thing you've ever known, whales, bears, elephants, yourself, was once this, a creature with fur, hiding in the dark, eating bugs and running from lizards. You're not descended from a tyrannosaur. You're descended from something that probably got stepped on by one, and that raises a question no dinosaur can answer. Is victory always loud? Or does the greatest success come not from standing on top of the food chain, but from slipping through its cracks? What does it take to win the ocean? Not just to survive in it or glide through it, but to dominate it, rewrite its anatomy, and become the blueprint for nearly every fish that would follow. In the Jurassic seas, something quiet happened. It wasn't a headline extinction, or a monstrous takeover by teeth and claws. It was subtler than that. The winners of the marine world didn't need fangs. They needed jaws that flexed, and bladders full of gas. They needed to bend, twist, dart, float, without spending all day fighting gravity or hydrodynamics. They didn't need to be terrifying. They just had to be efficient. And from that quiet anatomical revolution, a new fish was born. One so successful that today, more than 95% of all bony fish species, millions of shimmering finned things, trace their evolutionary lineage back to this moment. This is the story of the teleosts and the world they made, fin by fin. The Jurassic Ocean was not a calm place. For 100 million years it had been recovering from one extinction and anticipating the next. The Triassic seas had ended in chaos, an anoxic event, warming tectonic disruption. But by the early Jurassic, something new had stabilised. Shallow seas had returned, flooded by the slow drowning of continental margins. Coral-like reefs, mostly sponges and microbial mounds, had re-established themselves in the photic zones. Nutrient cycling rebounded, and in this warm, well-oxygenated, predator-filled soup, fish had room to try something new. Now, technically, teleosts weren't born in the Jurassic. Their origins stretch back further, perhaps into the late Triassic. But it was in the Jurassic that they diversified, radiated, and began to replace their ancestral cousins, the more primitive actinopterygians in earnest. The word teleost comes from the Greek for complete bone, which is a little misleading. What made them successful wasn't just their bone structure. It was a deep redesign of how a fish functions, from jaw to tail. Most earlier bony fish had relatively fixed upper jaws and rigid skulls. This made for strong bites, but limited feeding strategies. Teleosts, by contrast, evolved a kinetic skull, a jaw system with mobile elements. Their upper jaw could flex outward, creating suction as they opened their mouths. This meant they didn't have to bite chunks off prey, they could just inhale it. Small crustaceans, plankton, larvae, any living thing small enough to fit was now fair game. This method, called suction feeding, was fast, efficient, and energetically cheap. But that was only the beginning. They also refined their internal buoyancy system. Earlier fish had a gas bladder for flotation, but teleosts evolved a more sophisticated swim bladder, fine-tuned for vertical control. With this internal balloon of gas, they could hover mid-water, ascend or descend with tiny gas exchanges, and conserve energy that would otherwise be wasted battling gravity or surface tension. In short, they were agile, not just horizontally but vertically. A new kind of three-dimensional dominance. Their vertebral columns became more flexible, their fins became more manoeuvrable. Even their scales changed. Thinner, lighter, overlapping in new ways that allowed for smoother motion. The result was a fish that could turn on a dime, hide in reef crevices, lunge with explosive speed, or hover like a ghost. And in the wild ocean arms race, that kind of manoeuvrability became a survival trait of overwhelming importance. By the Middle Jurassic, teleosts were expanding into nearly every available niche in the marine ecosystem. Some fed on plankton, some became ambush predators, some cruised coral reefs, some sifted sediment. Fossil beds from Europe and China begin to reveal an increasing diversity of forms: slender torpedo shapes, deep-bodied reef fish, bottom feeders with downturned mouths. It wasn't a single lineage exploding. It was a whole architectural style of fish taking over, each tweak of jaw, spine, or fin unlocking a new way to live. And then there was Leedsichthys, a reminder that sometimes evolution still likes to show off. Leedsichthys problematicus, whose very name acknowledges the difficulty of understanding it, was one of the largest bony fish ever to exist. Estimates vary wildly. Some say 9 metres, others argue for 16. But even the lowest estimates make it bigger than a great white shark. And unlike the predatory giants of later oceans, Leedsichthys wasn't a hunter. It was a filter feeder, a slow-moving, wide-mouthed collector of plankton that glided through the Jurassic seas like a whale before whales. Its skeleton, like that of most large teleosts, was poorly preserved. Too cartilaginous, too delicate. But enough fragments have been found across Europe, especially in England's Oxford clay, to suggest its proportions, and more importantly its lifestyle. With gill rakers adapted to sieving plankton, and a mouth wide enough to gulp enormous volumes of seawater, Leedsichthys turned the productivity of the Jurassic plankton bloom into a body mass the size of a bus. It didn't need speed, it needed surface area. And thanks to the teleost blueprint, it got it. Why was the Jurassic Ocean so good to fish? Part of the answer lies in the stability of the climate. With no polar ice, warm temperatures at nearly every latitude, and a consistent stratification of ocean layers, the seas remained oxygenated and fertile. Upwelling zones brought nutrients to the surface. Phytoplankton bloomed. And where there is plankton, there are things that eat it, but Teleostis didn't just benefit from this system, they helped shape it. As mid-level consumers, they kept invertebrate populations in check, recycled nutrients, and served as prey for marine reptiles and early birds alike. They became the linchpin of the marine food web, not just in biomass, but in function. And with their diversity came resilience. If one lineage failed, another was already trying something new. If predators grew more efficient, teleosts outflexed them. Their evolution wasn't dramatic, it was patient, but relentless. What we don't know is almost everything. The fossil record of soft-bodied fish is notoriously difficult. Many early teleosts are known from compression fossils, two-dimensional impressions in limestone that tell us little about muscle, colour, or even true motion. The deep sea, where many modern teleosts thrive, is almost invisible to the Mesozoic record. And so what we do know comes from rare sites, accidental discoveries, and painstaking reconstructions. But what is clear, at least to the humble anatomist, is that the Jurassic marks a turning point. The ocean didn't just house fish, it began to belong to them, and not in the form of monstrous hunters or armoured titans, but in the quiet anatomical victories of suction jaws, kinetic skulls, and swim bladders. These were the upgrades that changed everything, and the descendants of those first Jurassic pioneers now make up the sardines in your sandwich, the goldfish in your tank, the tuna in your sushi, and most of the reef shimmering under sunlight. We look at fish today and forget their strangeness. The fins, the gills, the silent mouths. But their dominance is not accidental. It is ancient, and it began here, quietly, between the shifting currents of the Jurassic seas. So the next time you see a fish flick sideways in a tank, or vanish into a coral head, consider this. That flick is 190 million years old. A gesture inherited from a world where jaws loosened, bones lightened, and life learned that to survive the ocean, you didn't need to be the biggest, just the one that moved best, and in a world where everything floats, that was enough. What if time had a spiral shell? Not the ticking of seconds or the shadow of sundials, but a coil of calcium carbonate, curling tighter into the past with every turn. For paleontologists it nearly did, and in the grand, quiet seas of the Jurassic world, those spirals were everywhere. Before clocks, before calendars, before humans had even been imagined, the oceans were marking time with ammonites, soft-bodied predators encased in rigid logarithmic grace. Today, we trace them through stone. But back then, they swam, hunted, died, and drifted into the very geological strata that we now use to map the age of everything else. We start in the earliest days of the Jurassic period, just after the mass extinction that ended the Triassic. Around 201 million years ago, while the continents still clung together in Pangaea's slow dissolution, and the world's oceans surged with volcanic warmth, ammonites re-emerged, not as survivors, but as inheritors. Most of their earlier relatives had perished in the extinction event. What followed was an evolutionary rebirth so rapid and diverse that paleontologists have come to rely on ammonites like biological timestamps. New species evolved quickly, old ones vanished. Their shells fossilized beautifully, often preserved in limestone or shale with microscopic precision. And because they lived globally, in both shallow epicontinental seas and deeper marine basins, they left behind a stratigraphic legacy unlike any other extinct group. Ammonites were cephalopods, cousins to the squid and octopus, although they looked very different. Instead of soft, compressible bodies, they wore external armour, a coiled, chambered shell that acted both as protection and as a buoyancy device. The internal anatomy of an ammonite is something we mostly reconstruct from comparisons and fossil hints, but the basic layout is believed to have mirrored that of modern nautiluses, with a central soft body emerging from the open end of the shell and a series of gas-filled chambers extending behind. These chambers, separated by beautifully intricate walls called septa, were added sequentially as the animal grew. Each new chamber marked a former home the ammonite had once lived in, before sealing it off and floating onward. This internal architecture was not just elegant, it was functional. Ammonites adjusted the gas-to-liquid ratio in their chambers through a tube-like structure called the siphuncle, maintaining neutral buoyancy much like modern submarines. But unlike the living nautilus, which has relatively simple, curved suture lines where the septa meet the outer shell wall, ammonite sutures were extravagantly complex. Fractal-like, lace-edged, sometimes spiralling in elaborate fronds. These patterns weren't just beautiful, they provided structural reinforcement, allowing ammonites to build thinner shells without compromising strength. That meant faster growth, greater flexibility, and more room for evolutionary experimentation, and experiment they did. The Jurassic was an age of ammonite innovation. Coiling patterns varied from tight helices to flattened spirals, and even loosely twisted or irregular forms. Some were small enough to fit on your fingertip. Others, like the giant Parapuzosia, would eventually reach nearly 2 meters in diameter by the Cretaceous. But in the Jurassic, the average ammonite was the size of a grapefruit, darting through plankton-rich waters with a ring of tentacles and a sharp, beak-like mouth at its centre. Many likely had complex eyes, adapted to the dim filtered light of shallow seas. They were predators, feeding on small crustaceans, larvae, and sometimes each other. Their mobility, combined with a wide environmental tolerance, made them a foundational part of the marine food web. Strangely, ammonites left behind little soft tissue. What we know of their diet, behaviour, and even anatomy comes largely from fossilised impressions, coprolites, and indirect evidence. Occasionally, a jaw structure or ink sac has been preserved, offering fleeting glimpses into the biology of an animal that, for all its abundance, remains somewhat spectral in our understanding. It's an ironic fate for something so central to our reconstruction of deep time, the shells fossilised, the creature itself mostly gone, ghosts of their former selves spiralling in stone, but their true scientific superpower lies in biostratigraphy, the use of fossil organisms to date rock layers. Because ammonites evolved rapidly, had short lifespans, and were globally distributed, specific species can be tied to very narrow slices of geological time. This allows researchers to compare sediment layers from distant continents and synchronize their timelines. In effect, each ammonite species becomes a time marker. If you find a certain ammonite in a rock bed in England and the same species in a Moroccan limestone, you know those rocks are roughly the same age. No radiometric dating needed. No guesswork. Just the silent record of extinction and replacement, generation after generation, shell after shell. This is especially useful in the Jurassic, where marine transgressions, the rise of sea levels into continental interiors, created broad, shallow basins perfect for ammonite life and fossilization. Europe in particular became a fossil-rich seascape of lagoons and reefs, its modern-day chalk cliffs and clay beds layered with ammonite remains. Sites like Lyme Regis on England's Jurassic coast, or the limestone quarries of southern Germany, preserve them in astonishing detail. These places are time machines, their walls built from the slow accumulation of dead ammonites and the sediments that entombed them. What we don't know, or perhaps can't ever fully know, is how ammonites lived in terms of social behaviour, reproductive strategy, or daily life. Were they solitary? Did they swarm? Did their shell patterns serve camouflage, sexual selection, or nothing at all? We suspect that some had planktonic larvae, drifting for weeks before settling into benthic or pelagic lifestyles. We guess that predators like marine reptiles and early sharks hunted them frequently, and we've even found bite marks and cracked shells to support this. But as with so many extinct animals, much of their story remains speculative, a blend of sediment, inference, and the unfilled gaps of time. Yet their story feels oddly intimate. Ammonites mark not just geological stages, but the passage of extinction itself. They radiated after the end Triassic collapse. They thrived through warming oceans and spreading seas. They adapted to new coastlines, new pressures, new predators. And then, at the end of the Cretaceous, they vanished completely in the same impact that erased the non-avian dinosaurs. But unlike the dinosaurs, ammonites left behind a perfect breadcrumb trail, layer by layer, epoch by epoch, winding backward through time. Their extinction was not a mystery. Their lives are. And for all our scientific precision, there's something haunting in that. Maybe that's the real magic of ammonites, not just as fossil clocks or biostratigraphic markers, but as reminders of how time coils and uncoils without us. That even when the record is precise, the story may still be lost. That a spiral shell preserved in rock for 200 million years can outlive its maker and still whisper nothing, or maybe everything. We just have to keep listening. It is easy to think of vision as a straightforward thing. Light enters the eye, hits the retina, and a brain, assuming one is present, makes sense of it. But vision, especially in the deep past, was never that simple. It was a negotiation between biology and physics, between predation and survival, and sometimes it produced designs that seemed so over-engineered, so outlandishly complex that you wonder whether evolution was showing off. This is the story of Dolichoceras ingens, an animal most people have never heard of, despite having what may be the most advanced eyes in the history of life. Let's set the scene. Middle Jurassic. The warm, shallow seas of what is now eastern France. A calm carbonate basin, low in oxygen, high in preservation potential. Today we call it the La Vult-sur-Rhône Lagerstätte. But back then, it was a dimly lit underwater world filled with cephalopods, early fish and crustaceans, all drifting or hunting in the haze. And hiding in that world was Dolichoceras, an arthropod about 15 centimetres long, with a shrimp-like body, paddle limbs, and two of the most extraordinary eyes nature ever grew. Each eye of Dolichoceras had around 9,000 individual ommatidia. Those are the tiny optical units that make up a compound eye. That gives us 18,000 visual units across both eyes. For reference, a modern dragonfly, a famously agile hunter, has around 30,000. But it's not just the count that matters, it's the structure, the preservation, and the evolutionary context. These eyes were so perfectly fossilized that paleontologists could see the hexagonal facets still aligned like a honeycomb, wrapped around the convex curvature of the eyeball. Each ommatidium pointed in a slightly different direction, creating a panoramic field of view. But here's the catch. Unlike modern crustaceans that live in bright reefs or sunlit shallows, Dolichoceras lived in much dimmer conditions. That raises a question. What were these hyper-complex eyes for? Well, perhaps Dolichoceras was not a casual drifter. Its eyes suggest an active predator, one that needed fast, accurate motion detection in a twilight ocean. These compound eyes would have allowed it to track movement with incredible speed, detect contrast changes across wide fields, and lock onto prey in low light. And given the density of its ommatidia, it might even have seen in polarized light, something still common in mantis shrimp today. But again, these are inferences. We don't get to see what Dolichoceras saw, we only get the fossils. And a lot of very humbled speculation. Its body reinforces the theory. Flattened, with articulated swimming appendages and a flexible tail, it had all the gear of a fast swimmer. Its frontal appendages, preserved in exquisite detail, had long spine-like structures, clearly adapted for grasping or raking prey into its mouth. If you're building an ambush predator in the Jurassic Sea, this is not a bad design. See it, chase it, trap it, eat it. But then there's the strangest part. These eyes are preserved so well and in such detail because Dolichoceras lived in a place where oxygen levels were low enough to suppress scavengers and bacterial decay. It died in a time and place where most eyes would rot away. Its hypervision was frozen by anoxic luck. Which leads to an eerie irony. The most advanced eyes of the Jurassic are now blind. Perfectly preserved, perfectly useless. No longer hunting, just watching us back from the rock. It also leads us to a broader question. Why do compound eyes evolve this way at all? Why go through the trouble of building thousands of tiny optical units instead of one big lens, like ours? The answer, as usual, is trade-offs. Compound eyes have terrible resolution compared to vertebrate eyes, but they're amazing at motion detection and field coverage. They don't need a brain the size of a grapefruit to make sense of what they see. For a shrimp-sized arthropod, with limited processing power, this is the best system evolution could offer. Light, fast, wide, and effective. We often think of evolution as a straight climb, simple to complex, fish to philosopher. But Dolicharis is a reminder that complexity blooms in every branch. Sometimes it fades, sometimes it fossilizes, and sometimes it gets surpassed. Today there are no animals with eyes exactly like Dolicharis. Some stomatopods come close, but the design has mostly vanished. It was a moment in time, a visual experiment that worked brilliantly until the rules changed. Could there be a modern analogue? Not quite. The eyes of insects and crustaceans have followed different trajectories since the Jurassic, and while compound eyes are still common among arthropods, none seem to replicate this level of detail in such a small marine predator. It's as if Dolicharis built the sports car of compound vision, and then the factory closed. Still, the fossil record continues to surprise us. Every few years, another arthropod with uncanny optics turns up, and each one humbles us again. As of now, Dolicharis remains one of the best preserved examples of compound eye anatomy in the entire fossil record. And yet its behaviour, hunting style, and even precise classification are still debated. Was it more shrimp-like? Was it more like a swimming insect? What did it eat exactly? We don't know. We only know what the rock is willing to show us. That, in the end, is the lesson of paleontology. We are not reconstructing certainty. We are guessing, as carefully as we can, with bones and shells and ghosted outlines of eyes. And sometimes, if the mud is just right, we get a flash of something extraordinary. Something like Dolicharis. Something that saw the Jurassic seas in a way we never will. And it leaves us with this question. What else once watched this planet that we'll never see watching back? What's a shark supposed to look like before sharks looked like sharks? If you had to sketch one from memory, you'd probably draw something fast, torpedo-shaped, with gills slashed across the sides and rows of nightmare teeth inside a forward-facing mouth. And if you've seen rays, the so-called flat sharks of the modern sea, maybe you'd add in a flattened body, wide pectoral fins, and a bottom-sucking mouth. But the farther back you swim in time, the blurrier that silhouette becomes. Because long before great whites, before tiger sharks, even before most of the species we call rays, there was a fish that seemed to be practicing both forms at once. A creature with the body of a ray, the spine of a shark, and the scientific identity of a mystery. Welcome to the late Jurassic. Welcome to Protospinax. Roughly 150 million years ago, in the quiet lagoonal waters of what is now southern Germany, strange cartilaginous fish glided across the seafloor. The region would later fossilize into the famous Solnhofen limestone, a paleontological jackpot that preserved everything from jellyfish to the earliest birds with such detail that even soft tissue outlines remained. And in those still, shallow, oxygen-starved waters, Protospinax annectans left behind its ghost. Not teeth alone, though there were plenty, but entire flattened bodies, complete with fins, gills, and hints of musculature. Enough, at least, to confuse generations of scientists about exactly what it was, because Protospinax for a long time refused to fit. It had many of the characteristics associated with rays: broad, flat pectoral fins that merged into the head, a dorsoventrally compressed body, a mouth situated not at the front but underneath, and yet it also had characteristics that belonged squarely to sharks, not just teeth, but tail structures, vertebral arrangements, and a general spine and muscle system that refused to flatten out like a true ray. In fact, for over a century, its classification wandered between genera and families, flipped between ray ancestry and shark origin, often filed under uncertain affinities. Some even suggested it was a chimera, a prehistoric evolutionary hybrid that borrowed anatomy from both lineages but belonged to neither. Then, in the 21st century, something clicked. With more specimens, better imaging, and increasingly detailed comparisons across chondrichthyan fish, scientists began to reframe the mystery. Protospinax, it turns out, wasn't a primitive ray or an awkward shark cousin. It was likely an early offshoot on the stem group that would later give rise to rays and skates. A ghost cousin, not a direct ancestor. Think of it as a branch that split off early from the family tree before the modern lineages solidified. It retained some primitive shark-like traits, but had also evolved independently toward ray-like features. Not because it was trying to become a ray, but because evolution, when facing similar environments, often runs the same experiments. bottom-dwelling, flattened morphologies aren't an invention of rays alone. They've emerged in skates, flatfishes, guitarfishes, and even catfishes, all independently. The seafloor demands it. If you want to hide, ambush, or sift through sand, flattening out is useful. And so Protospinax, living in its quiet Jurassic lagoon, developed a body plan that looks modern, but isn't. It mimicked the flat look of modern rays long before true rays evolved. This is why Protospinax is so significant. Not because it's a common fossil, it isn't. Not because it's a perfect ancestor, it isn't that either. But because it reminds us how messy and non-linear evolution really is. The shark family tree isn't a clean triangle branching into rays and modern sharks. It's a thicket of experiments, most of which ended. Some left behind descendants. Some, like Protospinax, just left questions. Even the name is a puzzle. Proto means first. Spinax echoes an older shark genus. But Protospinax isn't the first anything. It's more like a late Jurassic side quest. And that suffix anectans means connecting. An ironic name, perhaps, because for decades it didn't clearly connect to anything. But now we see it as a connector in a deeper sense. A fossil that links not through ancestry but through analogy. It connects what was to what could have been. One of the reasons the story of Protospinax has gained attention in recent years is that it's forcing paleontologists to revisit their assumptions about the origins of modern rays and skates. For decades, the prevailing wisdom was that rays emerged directly from within the shark family, diverging sometime in the early Cretaceous. But if Protospinax really does sit outside both groups, not a ray, not a true shark, then that means the features we associate with rays may have deeper, more scattered roots. Flat bodies, enlarged pectoral fins, bottom feeding. These might not be inherited traits but convergent ones, evolved more than once in response to similar ecological pressures. And if Protospinax could evolve those traits so early, it means the potential for ray-like anatomy was lurking in the shark genome long before it was realised in modern lineages. Evolution doesn't invent from scratch. It tinkers, reuses, and occasionally loops back to ideas that almost worked before. Which raises a haunting question. How many Protospinax-like creatures have we never found? How many species independently tried to become rays or sharks, succeeded for a few million years, and vanished? The Solnhofen fossils are rare. Not every creature that died there left its body behind. And even among those that did, not every skeleton was preserved clearly enough to study. For every Protospinax we know, there may be 10 others we don't, half complete, lost to erosion, or simply buried where no paleontologist has looked yet. It's possible the shark ray debate would have ended decades ago if just one more fossil had surfaced. That's how fragile our reconstructions really are, but that fragility is part of the wonder, because each discovery like Protospinax doesn't just fill a gap, it opens a door. It reminds us that evolution is far stranger than the textbook diagrams suggest, that sometimes a creature looks like one thing, acts like another, and turns out to be neither, and that even in the well-studied rocks of Europe, you can find something that rewrites the story. So next time someone tells you sharks haven't changed in hundreds of millions of years, show them Protospinax, the shark that looked like a ray. That wasn't a ray. That wasn't even quite a shark. And yet, in its strangeness, told us more about both. And if you happen to drift off halfway through that fossil record, I put timestamps in the description, so you can always come back and pick up the thread, because the whole story is worth hearing. And as always, stay curious, stay calm. I'll see you in the next story. What does it take to survive since the Carboniferous? To crawl out of the swamps over 300 million years ago and never fully leave them? To endure mass extinctions, continental breakups, superheated atmospheres, and a planet overrun by reptiles? To live not in the spotlight of prehistory but in its damp, quiet shadows? This is the story of the amphibians who refused to die out, who hid, adapted, shrank, and clung on while everything else around them rose and fell. And it begins in the Jurassic. By the start of the Jurassic Period, somewhere around 200 million years ago, the ancient order of temnospondyls had already seen better days. These were the heavyweights of Paleozoic and early Mesozoic amphibians. Some grew over 4 meters long, others had skulls so wide they resembled coffee tables with teeth. For a long time, they dominated freshwater ecosystems. But by the time Pangaea began cracking apart, their reign was coming to an end. Climate was shifting, predators were evolving, and the massive amphibian body plan that once ruled the Carboniferous swamps was becoming a liability. One by one, the temnospondyl lineages began to vanish. Some limped into the Jurassic. Fossils in Africa and parts of Asia suggest a few managed to hang on into the early and even middle Jurassic, but they were relics, evolutionary ghosts in shrinking habitats. Their extinction wasn't abrupt, but it was inevitable. The world was warming, drying, and swarming with faster, more specialised reptiles. Large-bodied amphibians could no longer dominate. They could only hold on. And while the giants declined, something smaller was rising. The Jurassic period marks the first clear appearance of the 3 amphibian lineages that still exist today: frogs, salamanders, and caecilians. But the early members of these groups didn't look quite like their modern descendants. They were experiments, stubby-limbed, sharp-toothed, sometimes tailed, sometimes not, caught in evolutionary transition. Yet already they carried the basic blueprints of survival. Start with frogs. The oldest definitive frog fossil, Prosalurus betis, comes from the early Jurassic of North America. It was no pond dweller. Instead, it was a land-based jumper with long hind limbs and a light skeleton, small, agile, and built for escape. It had already evolved many of the skeletal adaptations that define frogs today: the fusion of certain bones, the elongation of the ankle, the absence of a tail. But it still retained a few primitive features like extra vertebrae. Prosalurus wasn't quite a frog, but it was no longer anything else either. Then there's Viorella, from Argentina. Slightly younger, possibly a true frog. Its fossils suggest a very similar body plan, short-bodied, broad-headed, capable of sudden propulsion. And there's Notobatrachus, another South American specimen, with characteristics that may link it to more modern frog families. The point is, by the mid-Jurassic, frogs weren't just surviving, they were diversifying. But frogs weren't alone. In the cooler, wetter environments of East Asia, another amphibian lineage was quietly taking shape: the salamanders. Their fossils are rare, but we do have evidence, especially from the Daohugu beds of northeastern China, of early urodels. The term urodel refers to modern salamanders, and some of their Jurassic relatives already showed signs of internal fertilization, regenerative abilities, and the signature long tail and walking gait. One such fossil is Beanerpeton jianpingensis, from the late Middle Jurassic. It had limbs positioned at the sides, a long body, and potentially even gills, suggesting a neotenic lifestyle, where juveniles retain larval traits into adulthood. This strategy, called pedomorphosis, is still common in modern salamanders like axolotls, but in the Jurassic, it was probably a lifeline. When predators got faster, being able to reproduce early, without leaving the safety of water, became an evolutionary insurance policy. And then there were the burrowers. Caecilians are perhaps the most mysterious of all amphibians. Today they resemble worms or snakes, with segmented bodies, no limbs, and sensory tentacles near their eyes. Their Jurassic ancestors were slightly less bizarre, but no less fascinating. One in particular, Echicelia micropodia, lived around 190 million years ago in what is now Arizona. It had tiny, stubby limbs and a broad, reinforced skull, perfect for digging. But what's most remarkable is that Eocacelia already had the internal features of modern caecilians: a reduced eye, an elongated body, and signs of a strong, flexible skull capable of burrowing through soil. It was not a surface creature. It lived in the dark, underfoot, far from the Mesozoic drama above, which may be exactly why it survived. Across these lineages, frogs, salamanders, caecilians, we see a pattern: survival through specialization. Frogs jumped, salamanders hid, caecilians tunneled, and all three, in their own way, abandoned the size and swagger of their temnospondyl ancestors. They became small, cryptic, and efficient. Their bones got lighter, their lifespans shorter, their reproduction faster. They learned to vanish, into ponds, into mud, into time. And that invisibility may have saved them, because unlike the dinosaurs, the crocodiles, or even the early mammals, Jurassic amphibians never competed for dominance. They fill the ecological niches that were easy to ignore. The insect catchers, the leaf lurkers, the puddle dwellers. They weren't trying to rule the planet, they were just trying not to die. And somehow, they didn't. Today, amphibians are among the most endangered vertebrates on Earth. But they're also among the most ancient. Every time you hear a frog call, or see a salamander under a log, or imagine something squirming in the soil beneath your feet, you're witnessing a survival story that began long before the first flower bloomed. Long before birds flew, long before mammals rose, the Jurassic was their quiet crucible. And it leaves us with this question. In a world obsessed with dominance, what can we learn from the creatures that just endured? And that endurance is not just biological, it is anatomical, behavioural, even philosophical. A kind of slow, stubborn persistence written into the bones. Amphibians do not aspire. They do not colonize continents or reshape ecosystems. They persist through constraint. Their skin must remain moist. Their eggs cannot survive far from water. Their lungs are simple. Their metabolism's modest. Their needs almost insultingly small. But those very limitations, the things that seem to make them fragile, are precisely what kept them going. Because when the Earth changes, when climates swing or continents drift or seas invade, the ones already living at the edge of survival don't have far to fall. In the fossil record, this creates a kind of invisibility. Amphibians rarely make headlines. They don't leave massive skeletons or armoured skulls. They don't fossilise well, but occasionally, just often enough, a sliver of their past surfaces, a jawbone in mudstone, a pelvic arc in limestone, and with each fragment we piece together a portrait not of dominance, but of endurance, the kind that doesn't need to be seen to succeed. What makes this even more remarkable is that amphibians were doing this in a world increasingly unsuited to them. The Jurassic was a greenhouse Earth. Temperatures were high, rainfall was seasonal, rivers were shifting, coastlines were unstable, and reptiles, especially the aquatic ones, were everywhere. Amphibians had every excuse to give up, but instead they adapted in miniature. Frogs reduced their larval stages, salamanders learned to regenerate, caecilians vanished underground altogether. Evolution doesn't reward ambition, it rewards fit, even if that fit looks like hiding. And maybe that's the haunting truth at the heart of their story. That success isn't always loud. That survival isn't always glorious. Sometimes it looks like a tiny jaw under a leaf, or a translucent egg in a puddle. Sometimes it's the faint ripple of something that hasn't changed in 200 million years, except to become even quieter. These creatures do not ask to be remembered, but they are. In fossils, in field guides, in rain-soaked forests and urban ditches. The Jurassic didn't just give us giants, it gave us whispers, and somehow they're still echoing. When did mammals stop waiting for their turn? It's easy to think of the Jurassic as a time when mammals were simply biding their time. Small, soft-bodied things lurking in the dark, waiting for the dinosaurs to get out of the way. For decades, that was the image. Shrew-like creatures hugging the forest floor, unnoticed, unimportant, unambitious. But like most evolutionary myths, that one doesn't hold up. Because even in the middle of the Jurassic Period, long before mammals took over the world, they had already started branching into niches no one expected them to. They didn't wait. They adapted. Start with the swimmer. Roughly 164 million years ago, in what's now the Daohugu beds of northeastern China, a creature named Castrocauda lutrasimilis left behind the kind of fossil that makes paleontologists stare for hours. It wasn't just the bones, it was the impressions. You could see the outline of fur, you could see webbed feet, even the suggestion of a tail flattened like a paddle. Here, at last, was a Jurassic mammal that didn't look like a mouse. It looked almost like an otter. And it wasn't small, not by Mesozoic standards. Most mammals of the time were the size of mice or smaller, but Castrocauda stretched over 40 centimetres in length. It had strong hind limbs, broad feet, and that thick tail, all adaptations for an aquatic lifestyle. And most impressively, it had specialised teeth. Not just generalised molars, but long, backward-pointing cusps ideal for gripping slippery prey. This was no insectivore. This was a predator, probably fish-eating, possibly nocturnal, but definitely not waiting its evolutionary turn. Then there were the gliders. In roughly the same beds where Castorocada was found, another fossil emerged that pushed expectations even further. It was called Vellaticitherium antiquum, and it had wings, not feathered ones, not leathery ones, but a membrane of skin stretched between elongated limbs and digits, much like a modern flying squirrel or colugo. Its bones were delicate and light, its limbs long and grasping, and its tail, partially preserved, was likely flattened for steering. It was, in essence, a Jurassic glider, one that lived in the treetops, feeding on insects, launching itself from branch to branch in a forest full of towering conifers and the occasional hungry pterosaur. These aren't isolated cases. They're part of a broader picture emerging from middle to late Jurassic fossil beds, particularly in China, where volcanic ash and fine lake sediments preserved mammals in extraordinary detail. We see hints of burrowers, diggers, climbers, and even semi-arboreal omnivores. The classic image of the Jurassic mammal as a generic shrew is quickly unravelling. In its place, a miniature world of ecological diversity. Mammals were already occupying specialised roles. They were already experimenting with form and function. And while they never challenged the dominance of dinosaurs, they weren't ignored either. They were evolving under the radar, and maybe that's the key. Mammals didn't survive by being loud. They survived by being flexible, by filling the cracks, by moving into the places the big reptiles didn't care to go, underground, underwater, up trees. This wasn't a strategy of conquest. It was a strategy of resilience, and it paid off. Even the structure of these early mammals hints at how much was already in place. Their inner ears were more complex than their non-mammalian ancestors. Their jaws were tighter, more precise. Their fur, though only fossilised in rare conditions, was already likely ubiquitous, not just for insulation, but for thermoregulation in variable climates. And their reproduction, while still not fully understood, may have already involved some degree of parental care. These were not just miniature reptiles, they were mammals through and through, and yet they remain mostly invisible in the public imagination. Ask someone to name a Jurassic animal, and they'll say Stegosaurus, or Allosaurus, or maybe Brachiosaurus. They won't say Castorocauda. They won't picture Vellaticitherium launching silently through ancient trees. But perhaps that's fitting, because these mammals, and their quiet evolutionary success, weren't about spectacle. They were about persistence, innovation, and strange, sometimes whimsical adaptations that told the world, we're here too. So next time you look at a river otter sliding through a stream, or a flying squirrel gliding from branch to branch, or a shrew twitching in the underbrush, remember this: their story didn't begin after the dinosaurs. It began beside them, beneath them, and sometimes even above them. They didn't wait. They adapted, and maybe that's why we're here at all. And the fossil record from this time, though fragmentary, keeps surprising us. In Portugal, in the Kimmeridgian Age sediments of the Guimarota coal mine, paleontologists uncovered one of the richest late Jurassic mammal assemblages known in Europe. Dozens of tiny jaws and teeth, perfectly preserved in the dark shale, revealed a miniature ecosystem hidden in the undergrowth, one teeming with dryolistids, multituberculates, and other strange names that never quite made it into children's dinosaur books. But these weren't evolutionary leftovers. They were busy. They were specialised. Some had teeth adapted for gnawing tough seeds. Others had molars that hinted at omnivory, or at an insect diet with alarming efficiency. Multituberculates in particular deserve a moment. They are often described as the rodents before rodents, though they weren't rodents at all. They just happened to evolve something similar. Long incisors, complex molars, a gnaw and grind feeding strategy that would become wildly successful again, tens of millions of years later. Some multituberculates even show evidence of prehensile tails and flexible ankles, hints of life in the trees, perhaps clambering over conifer branches, dodging pterosaur shadows, and gnawing on cone seeds long before squirrels ever existed. All of this points to one thing. Mammals weren't passengers in the Jurassic. They were participants, just not the kind that left giant footprints or dramatic bones. Their evolutionary canvas was subtler, smaller, more intimate. It was drawn in nerve endings and ankle joints, in the wear patterns on tiny teeth, in the curve of a wrist built for grabbing bark instead of running from it. And that subtlety is easy to miss, but it's also a lesson. In the long history of life, dominance is often temporary. Flexibility, on the other hand, leaves a legacy. The mammals of the Jurassic weren't waiting for permission to innovate. They were already doing it. In fur and flight membranes, in underground tunnels and mid-canopy glides. They were rehearsing a world that didn't yet belong to them, but one day would. No one told them it wasn't their time, they just got to work anyway. How do you sneak flight into evolution without anyone noticing? It didn't happen with a flap, or a takeoff, or some triumphant moment when a dinosaur leapt into the air and became a bird. It happened quietly, feather by feather, bone by bone, over millions of years, and for most of that time, no one was flying. Not yet. But the blueprints were being drafted anyway, on the arms of tiny predators, in the tails of gliding climbers, in the filaments of creatures that still hunted on foot. If you were alive during the late Jurassic, around 160 million years ago, you would not have seen birds, but you might have seen something close, something strange, something halfway, and it might have looked back at you. Feathers, it turns out, are older than flight. Much older. They probably didn't start as tools for flying at all. The earliest feathers we know of, not just from bones but from preserved impressions, show up in fossils like Anchiornis, a crow-sized animal from what is now northeastern China. This creature, with its long tail, toothy snout and feathered limbs, didn't fly in any way we'd recognise. It could possibly glide, or at least slow its descent. But its feathers weren't just aerodynamic tools. They were display features. They were insulation. They were perhaps for balance. Feathers started as something else, and only later became wings. That evolutionary retooling wasn't rare. Evolution almost never invents things from scratch. It reuses, repurposes, reconfigures. In the case of feathered dinosaurs, it worked with what it had. Small, lightly built theropods already adapted for fast movement, with hollow bones and three-fingered hands. Then it began adjusting the recipe. Longer arms, stiffer tails, lighter skulls, more asymmetrical feathers. Eventually something like lift. One of the most famous fossils in the world marks this halfway point. Found in the Solnhofen limestones of Germany, in layers dating back about 150 million years, Archaeopteryx is often called the first bird. That's not quite right. It's not fully bird. But it's also not just dinosaur. It's perched on the evolutionary threshold, wearing a mosaic of traits that seemed impossible when it was first discovered. Teeth in its beak, claws on its wings, a long bony tail, but also real flight feathers, asymmetrical veins, lightweight skeleton, a wishbone. Not built for long flights perhaps, but likely capable of short flutters or glides between trees, and it wasn't alone. Fossils from the Tiaojishan Formation in China began revealing an entire community of feathered dinosaurs, Xiaotingia, Orornis, Eosinopteryx, each with different combinations of traits, some more bird-like, some less. Some with long legs, others with long tails, still others with ornate head crests or double layers of feathers. The diversity was startling, and it blew open the idea that there was a clean line between bird and not bird. There wasn't. There was a tangled bush, a radiation of experiments in size, shape, and feather architecture. This complexity has made the origin of flight one of the most debated topics in vertebrate paleontology. Did these animals launch from the ground up, flapping their arms for extra thrust as they ran? Or did they begin in the trees, using feathered limbs to control gliding falls? The evidence leans gently toward the latter, an arboreal origin, but no answer is final. What we do know is that flight didn't appear in a vacuum. It emerged from ecological pressures, predators chasing prey, prey escaping predators, animals clambering through trees, courting mates, staying warm. Flight wasn't an invention. It was an escalation, and for every name that made it into textbooks, there were likely dozens of species we've never found. Their feathers decomposed, their bones scavenged, their fragile forms erased before they could fossilize. But the ones we do have, thanks to perfect circumstances of lakebed sediment, low oxygen, and volcanic ash, whisper a truth far stranger than anything we imagined in the early 20th century. That dinosaurs didn't just give rise to birds, some of them already were birds, long before the definition caught up, and that raises a quiet, haunting question. What else are we missing? If feathers could exist for millions of years before anyone noticed their real purpose, what other tools is evolution hiding in plain sight? What complicates things further and makes it infinitely more fascinating is how familiar yet alien these animals seem. Take Anchiornis, for example. It had not 2, but 4 wings. Feathers stretched not only across its arms, but also along its legs. Imagine that for a moment. A dinosaur with winged legs. This isn't some poetic metaphor, this is preserved fact, visible in dozens of stunning specimens from Liaoning province. Its skeleton says theropod, but its silhouette, soft with contour feathers and downy edges, says something else entirely. It was an animal on the edge of an evolutionary precipice, half falling, half fluttering. The term bird starts to lose meaning here, at least as a fixed category. Because the traits we associate with birds, like feathers and wishbones, didn't appear all at once. They emerged gradually, unevenly, like a constellation forming over eons. Each dot on its own doesn't tell the story, it's the pattern that matters. And that pattern is one of deep experimentation. Even the bones tell tales of change. Asymmetry in feathers hints at aerodynamic function. Elongated arms suggest flight strokes, but other traits, like the presence of claws on wings or tails used more for balance than for steering, remind us these were not fully avian. These were experiments, some successful, some short-lived, all of them part of the long winding story of how dinosaurs stopped just walking and started taking to the air. And perhaps the most beautiful part of that story is this. It didn't happen for a reason. There was no master plan, no goal of flight. These animals didn't know they were becoming birds. Evolution just kept tweaking the variables. A little more lift here, a slightly lighter bone there, more vein structure on one generation's feathers, then more again. Until eventually lift outweighed gravity, and the air, once a boundary, became a possibility. We think of flight as triumphant, but its origins were quiet, awkward, probably a little ridiculous. A series of half-glides and flapping tumbles in forest shadows. Nothing majestic, nothing cinematic, just life, adapting to a new dimension one feather at a time. And in that awkwardness, there's something profoundly human. Because we too come from a lineage of accidents that somehow worked, of traits repurposed, of bones that used to be something else. The miracle of flight wasn't magic, it was persistence. And it started, long ago, with a dinosaur that didn't quite know what its feathers were for. What was crawling through the Jurassic leaf litter, while dinosaurs roared above? Most stories from this era look up, at the sky, at the towering necks of sauropods, at the wide shadows of pterosaurs gliding over tidal flats. But if you lower your gaze, all the way down, to where the roots curl and the dead leaves pile up, there's another world entirely, smaller, colder, quieter. And from this underfoot domain came some of the most quietly successful animals of all time. Lizards, and something even more peculiar, a lineage that began to trade legs for flexibility. A prelude to what we now call snakes. They weren't dramatic and they weren't large, but they were everywhere. To understand this quieter chapter of the Jurassic, we need to look at the group called squamates, the branch of reptiles that today includes all lizards, snakes and amphisbaenians. Their origin story is murky, shadowed by poor fossil preservation and the fragility of small bones, but molecular clocks and a growing trickle of fossil evidence now suggest that squamates were already well underway by the Middle Jurassic. Not abundant, not yet dominant, but present, hidden in the leaf litter darting between rocks, feeding on insects while the giants passed overhead. Among the earliest known representatives is a slithering enigma from what is now Portugal, Portugalophis lignites. It dates to around 150 million years ago. It was long-bodied, limbless, and tiny, just a few centimetres wide. Its vertebrae show unmistakable affinities with snakes, but it lived in a world before snakes, as we know them existed. This was not a venomous constrictor or a tree-dwelling predator. This was something basal, something transitional, possibly burrowing, possibly aquatic. It had started down the path of limb reduction, a path taken independently by many squamate lineages, but most dramatically by the ones that would someday evolve into true snakes. Why would a reptile give up its limbs? In part because the world beneath the world is narrow. Tunnels, crevices, root networks. These are places where legs get in the way. Limbless movement allows for sliding into the smallest gaps, twisting through soil with minimal resistance. It's not a weakness, it's an adaptation. One that's been made again and again across geologic time. And in the Jurassic, some reptiles were already exploring it. But not all squamates followed that path. Others took to trees, or stayed on the forest floor, developing longer limbs, better gripping toes, more acute vision. They fed on insects, small vertebrates, eggs. Some may have used camouflage or bright coloration to communicate or intimidate, though we can only guess. The diversity of form was already beginning to branch, and that branching has never stopped. Even though the fossil record for early lizards is notoriously spotty, fragmentary remains suggest that small squamates were dispersed across Laurasia by the late Jurassic. Some may have come from earlier Triassic ancestors, others were new offshoots. Their names are technical, things like Ixtatosaurus, Parviraptor, or Dorsetisaurus, but their story is simple. They were survivors. They lived small, reproduced fast, and avoided the spotlight. They evolved in the cracks, literally and evolutionarily, and they've been with us ever since. What's humbling is that we almost missed them. For decades, paleontology focused on the big bones, the skulls you could mount, the claws you could point to. But as techniques improved, especially micro-CT scanning and fine sediment preparation, we began to notice the overlooked, the wrist bones in a scrap of shale, the telltale vertebrae in a matrix once ignored, and each new discovery adds a pixel to a much wider picture. That the Jurassic wasn't just the age of giants, it was also the age of beginnings, quiet ones, small ones, reptilian ones, and somewhere in that leaf litter, a small scaly thing turned its head. It listened, it watched, it waited. It didn't have fans or fame, it didn't even have a name yet, but it would. One day. Because you don't have to be tall to outlive a sauropod, you just have to survive. And survive they did, not through strength, but through strategy. These early squamates weren't just lucky stowaways on the arc of evolution. They were adaptable, opportunistic, and deceptively advanced. Some developed hinged jaws that allowed them to grab and swallow larger prey. Others evolved flexible skulls, letting them manipulate food in intricate ways. While their skeletons remained delicate and hard to fossilize, their anatomical innovation was anything but fragile. These weren't just lizards in the modern sense, they were blueprints. Some were arboreal climbers with grasping limbs, others were burrowers, with thick skulls and reduced eyesight, testing out subterranean life before it became fashionable. The ecological roles they played were quiet but essential. By preying on insects, eggs, and small vertebrates, they helped control population booms. By serving as prey for larger creatures, they fed the chain upwards. They moved between niches without fanfare and often without notice. But over time, their presence reshaped ecosystems. The Jurassic forest floor wasn't just a dumping ground for leaf litter. It was a living web, and these squamates were the threads between worlds too small to see from above. One of the most remarkable things about this group is their long evolutionary patience. Unlike the dinosaurs, who would explode into spectacular forms and then crash spectacularly at the end of the Cretaceous, squamates played the long game. Slowly, methodically, they diversified, they miniaturized. They found ways to fit into every ecosystem. Tropical, temperate, arid, forested, even aquatic. Some lineages died out, others kept going. A few, like the lineage that includes Portugalophis, quietly laid the groundwork for entire categories of future reptiles, and all of this unfolded beneath our feet. If you picture the Jurassic in your mind's eye, it's easy to get distracted by the giants. They're cinematic, they're iconic, but they're not the whole story. They're not even most of the story. Because for every ton of sauropod muscle, there were thousands of grams of squamate cunning, reptiles with no interest in towering necks or bone-crunching jaws, just the cleverness to disappear. to hide, to wait, and maybe that's what's most enduring about them. Their story reminds us that not all success is loud, that the things which shape the future often start at ankle height, hidden in bark, in soil, in silence. The dinosaurs roared above, but the basement reptiles, they listened, and they outlasted the noise. Were those backplates a weapon, a radiator, or a fashion statement? Sometimes, evolution makes choices that look like performance art, and nowhere is that more evident than in the strange, spiked and stubbornly slow-moving creatures we call stegosaurs. If Jurassic Park made them famous, paleontology has made them confusing, because the more we uncover, the less we agree on what those magnificent dorsal ornaments actually did. The stegosaur body plan is instantly recognisable. Low-slung torso, arched back, long tail, and a double row of bony plates that look like someone built a folding fan out of keratin and rage. These animals belong to the thyreophorans, the armoured dinosaurs, a group that had already begun experimenting with body armour much earlier. But stegosaurs took that concept in a uniquely dramatic direction. Their lineage emerges in the Middle Jurassic, around 170 million years ago, and by the late Jurassic they were well distributed across what is now North America, Europe, Asia, and possibly Africa. Stegosaurus itself, the most famous of the bunch, lived around 150 million years ago in what's now Western North America. It was about the size of a bus, had a head the size of a watermelon, and a brain that some researchers have politely described as modest. But what it lacked in cranial capacity, it made up for in osteoderm spectacle. Let's talk about those plates. They weren't just stuck on like spines. Each one was embedded in the skin, anchored by connective tissue, and riddled with a network of blood vessels. This vascularization has led to decades of debate. Were they thermoregulatory structures, essentially biological radiators to help dump excess heat? Or were they display structures, signalling sexual maturity, fitness, or species identity? Or perhaps they were defensive, a way to make the animal look larger, more intimidating, or simply harder to attack? The answer may be yes, to all of it. The thermoregulation hypothesis is elegant. The plates, with their thin profile and wide surface area, could theoretically act as heat exchangers. In cooler morning hours, they could absorb sunlight and help warm the body. In the heat of midday, blood could be redirected away from them, or flushed through to dissipate heat. This theory has been supported by computer modelling and vascular structure analysis. But it doesn't explain everything, because stegosaur plates are highly variable. Even between individuals of the same species, some are rounded, some are sharply pointed. Their number and shape vary dramatically. If heat regulation were the only purpose, you'd expect more uniformity. And that's where the display theory enters. In some species, the plates were asymmetrical. In others, they seem to be arranged with a visual rhythm that suggests a kind of natural billboard, a silhouette meant to be seen. Not necessarily by predators, but by other stegosaurs. This is where sexual selection might come in. Like peacock feathers or deer antlers, the plates could have been a costly signal. An elaborate trait that says, I'm healthy enough to waste energy on growing these things. Mate with me. It's not a far-fetched idea. Evolution has repeatedly rewarded animals that are unnecessarily extravagant if it helps their genes get passed on, but defense hasn't been ruled out either. Even if the plates themselves weren't sharp or strong enough to repel a predator directly, their presence could have changed the outline of the animal, making it harder to bite or more intimidating to approach. And of course, the tail was where the real defense lived. Stegosaurs didn't just have tails, they had thagomizers. Yes, that's the actual term, borrowed from a Gary Larson cartoon and adopted, with a surprising lack of resistance, by professional paleontologists. The thagomizer is the set of paired spikes at the end of the stegosaur's tail, usually 4, angled outward, and likely capable of inflicting serious damage. Evidence of puncture wounds in theropod fossils suggests that these weren't just for show. Stegosaur tails were flexible, muscular, and likely used as active deterrents. So while the plates may have been ambiguous, the spikes had a point. Stegosaur diversity, though often overlooked, was genuinely impressive. In China, Tuojiangosaurus sported taller plates and a more compact body. In Africa, fragmentary remains hint at forms that may have been more basal. In Europe, Dacentrurus and Lexovisaurus added regional flair to the family tree. They weren't a monolith, they were a radiation, a whole subculture of armoured browsers, each experimenting with different osteoderm designs. And they weren't just armoured. They were also survivors. For tens of millions of years, stegosaurs held their ecological ground. Mid-sized herbivores, feeding on low vegetation, slow to move but difficult to kill. Their teeth were small, their bite weak, but their gut likely enormous. A fermentation chamber that did most of the work for them. They lived slowly, they died hard. But by the end of the Jurassic, something shifted. Climate, competition, habitat. We're not sure. But stegosaurs began to decline, and by the early Cretaceous they were gone. Their spiky cousins, the ankylosaurs, would carry the armoured legacy forward. But the plate-backed originals had vanished. Still, they left a fossil record as dramatic as their anatomy. Whole skeletons, skin impressions, bone beds with multiple individuals, and of course, the lingering mystery. Why the plates? Why that body plan? Why evolve something that looks like it belongs in a medieval illustration of a dragon? Maybe we're asking the wrong question. Maybe it wasn't about utility at all. Maybe it was about visibility. Because in a world of giants, sometimes the only way to matter is to be strange enough to be noticed. This is where sexual selection might come in. Like peacock feathers or deer antlers, the plates could have been a costly signal. An elaborate trait that says, I'm healthy enough to waste energy on growing these things. Mate with me. It's not a far-fetched idea. Evolution has repeatedly rewarded animals that are unnecessarily extravagant if it helps their genes get passed on. But defence hasn't been ruled out either. Even if the plates themselves weren't sharp or strong enough to repel a predator directly, their presence could have changed the outline of the animal, making it harder to bite or more intimidating to approach. And of course, the tail was where the real defence lived. Stegosaurs didn't just have tails, they had thagomisers. Yes, that's the actual term, borrowed from a Gary Larson cartoon and adopted, with a surprising lack of resistance, by professional paleontologists. The thagomiser is the set of paired spikes at the end of the stegosaur's tail, usually 4, angled outward, and likely capable of inflicting serious damage. Evidence of puncture wounds in theropod fossils suggests that these weren't just for show. Stegosaur tails were flexible, muscular, and likely used as active deterrents. So while the plates may have been ambiguous, the spikes had a point. What happens when evolution designs a medieval tank too early? In the late Jurassic, while predators got faster and herbivores got taller, one lineage of dinosaurs took a different approach. They didn't run, they didn't tower, they stayed low, squat, and stubborn, turning their bodies into fortresses. These were the first ankylosaurs. And while the club-tailed giants of the Cretaceous would someday steal the spotlight, their Jurassic ancestors, the nodosaurs, were already experimenting with armour systems that made anything with teeth think twice. These weren't your average spike-covered reptiles. Nodosaurids developed their protection from the inside out. Their skin was reinforced with osteoderms, bony deposits formed within the dermal layers, creating a kind of natural chainmail. Some were flat, others were keeled. Many were arranged in complex overlapping patterns, like shingles on a reptilian roof. Their entire evolutionary strategy could be summed up in one principle. You can't eat what you can't get your teeth around. In North America, around 150 million years ago, this philosophy was already well underway. The Morrison Formation, famous for its towering sauropods and carnivorous all-stars, also gave us Gargoylosaurus, one of the earliest well-preserved ankylosaurs. Despite its fearsome name, it was only about 3 meters long, but what it lacked in size it made up for in defensive commitment. Rows of tall, narrow spikes lined its neck and shoulders. Its skull was low, wide and armoured, complete with bony eyelids. Its back was covered in nodules and plates. And crucially, unlike later ankylosaurs, it had no tail club. That absence is important. It reminds us that the iconic club wasn't part of the original plan. These early ankylosaurs were relying not on offensive weaponry, but on passive defence. Their armour was their message. You can try, but it's going to be annoying. And sometimes, annoying is enough to survive. Another remarkable example is Memura pelta, discovered in Colorado and dated to roughly the same time. Though more fragmentary than its gargoyle-named cousin, Mimura pelta shows similar trends: robust limb bones, low slung body, and extensive dermal armour. It likely had spines along its flanks and small leaf-shaped teeth for cropping low vegetation. If Gargoylosaurus was a cactus, Mimura pelta was a living barricade. But these animals weren't just walking shields. Their evolutionary success hints at something more subtle: the niche of the well-defended grazer. In a landscape ruled by toothy theropods like Allosaurus and Ceratosaurus, being armoured wasn't optional. It was survival. Ankylosaurs didn't need to outrun their enemies, they just had to make biting them not worth the effort. There's a quiet elegance to this strategy. It suggests a world where speed and power weren't the only answers, where patience, persistence, and plate-thick skin were just as effective. In many ways, the nodosaurs were preemptive solutions to problems the ecosystem hadn't even finished inventing yet. They were early drafts of an idea that evolution would keep revising, until it became so over-engineered that even apex predators learned to walk away. And yet, for all their armour, these Jurassic ankylosaurs are surprisingly hard to study. Their skeletons are rare. Their bones, often fused and flattened, don't preserve as easily as others. And their fossils are usually found in isolation. A single skull here, a torso there, a scattering of plates with no map to place them. Reconstructing their lives means piecing together not just anatomy, but behaviour. What did they eat? How did they move? Were they solitary? Did their armour grow with them? Did they bury themselves for warmth, or coolness, or concealment? We don't know. And that's okay, because science isn't about knowing everything. It's about knowing how little we know and asking better questions. Each armoured fossil is a whisper from a world that no longer exists, a world where defence was design, and survival meant blending into the undergrowth while predators roared overhead. So next time you see a tank on tracks, or a rhinoceros, or even a heavily defended tortoise, remember, the idea isn't new, the strategy isn't modern, it's ancient, it's Jurassic. And long before the Cretaceous arms race gave ankylosaurs their clubs, the nodosaurs had already made their case. You don't have to be fast, you just have to be too annoying to eat. What did it take to become the biggest thing that ever lived? The answer didn't arrive all at once. It didn't thunder into the Jurassic with a 50-ton footprint or a whiptail crack through the canopy. It tiptoed in, quietly, on 4 sturdy legs, and it looked a little awkward. Long before the age of titanic sauropods like Diplodocus or Brachiosaurus, their ancestors were still figuring things out. How to hold up a neck that didn't stop growing, how to shift from 2 legs to 4, how to eat from both the treetops and the underbrush without toppling over. In the early Jurassic, between 200 and 180 million years ago, evolution ran a series of experiments. The result was something that didn't yet tower over the landscape, but definitely loomed. One of the earliest of these experiments was Volcanodon. Found in the rocks of what is now Zimbabwe, Volcanodon lived sometime near the beginning of the Jurassic, and it marks a strange moment of transition. It still carried traces of its bipedal ancestry, a slender build, relatively long hind limbs, but had already shifted toward quadrupedal movement. Its limbs were strong and columnar, its tail was muscular, its body was already expanding into the barrel-chested form we'd later associate with full-size sauropods. But Volcanodon wasn't enormous, not yet. It measured maybe 6 or 7 metres. Large for its time, modest compared to what came later, but size wasn't the point, not yet. The real innovation was posture. Quadrupedalism may not seem revolutionary, but for an animal with a long neck and even longer aspirations, walking on all fours offered a solution to a delicate balancing act. How to support both a body stretched forward and a tail stretched backward without putting strain on either. This balance was the first major engineering breakthrough on the road to gigantism, and it didn't happen just once. In the early Jurassic of what's now southern China, a genus called Unanosaurus was solving the same problem in its own way. Unlike Volcanodon, Unanosaurus retained more gracile theropod-like features. It may have walked on 2 legs at times, especially when young, but its forelimbs were growing stronger, its teeth better suited to raking vegetation, and its vertebrae showing signs of the sauropod future. Unanosaurus wasn't a true sauropod, but it was close, part of the broad and branching family tree that led to them. Together, These creatures represent a moment of biomechanical trial and error. Not yet giants, not yet herd-moving, continent-wandering browsers, but no longer the agile, fast-running bipeds of the Triassic either. Something was shifting, slowly, massively, and the environment was ready. The early Jurassic was humid, swampy. Pangaea was beginning to split, and with it came rift valleys and new ecological niches, fern prairies, river floodplains, conifer-dotted woodlands. These were landscapes where a large, slow-moving grazer could thrive, and so the experiment continued. Necks stretched longer, limbs grew thicker, air sacs may have begun to evolve, lightening the skeleton and improving breathing efficiency. Teeth diversified, some spoon-shaped, others pencil-thin, suggesting different feeding strategies even among early sauropod cousins, and most importantly, body plans standardized around something simple. Be big, be stable, and don't fall over. But what really made sauropod gigantism possible wasn't just anatomy, it was time. Given enough generations, evolution isn't in a rush. A few centimetres here, a vertebra elongating there. Over millions of years, small innovations accumulate until they become paradigms. The early Jurassic didn't feature the giants we now picture, but it featured the decisions that made giants possible, and those decisions were remarkably conservative. Sauropods, once they found a working blueprint, stuck with it. Over the next 100 million years, they would get bigger, more specialised, more regionally diverse, but the core idea stayed the same. Walk on 4 legs, keep the neck long, digest slowly, eat everything. It's easy to focus on the showstoppers, the 70-ton colossi of the late Jurassic and Cretaceous, but without Volcanodon or Unanosaurus, without the quiet pioneers who tested what a long neck and a low centre of gravity could do, that future never would have arrived. So if you ever feel small, or slow, or like you're not making much progress, remember this. The biggest things in Earth's history started small too, and sometimes just standing on 4 legs instead of 2 can change everything. But size, as with all things evolutionary, comes at a cost. The larger an animal becomes, the more resources it needs, the more heat it retains, and the more biomechanical stress it places on its own skeleton. Early sauropods were not simply scaling up their Triassic ancestors. They were engineering around these new realities in ways that still fascinate biomechanists today. One of the earliest adaptations was vertebral architecture. The bones along the neck and spine of these creatures were not solid. They were riddled with air spaces, a structure known as pneumaticity, which reduced weight while maintaining strength. This wasn't just about making the animal lighter. It was about managing balance, oxygen flow, and even thermoregulation. These internal air sacs likely connected to the lungs in ways that parallel modern birds, suggesting that sauropods may have had an efficient one-way breathing system long before such features were perfected in flight. Another underappreciated innovation was foot structure. Unlike many reptiles, sauropods didn't splay their limbs outward. Their legs were pillar-like, positioned directly beneath the body like columns in a building. And at the bottom of these columns were feet uniquely adapted for carrying weight. The metatarsals of the hind feet were arranged in an arch, distributing load across a broad surface, while the forefeet were digit-reduced, often forming a horseshoe-shaped column. These were not running feet. They were load-bearing platforms, engineered for mass, not speed. Then there was the gut. To process the massive volumes of plant matter needed to sustain such bulk, early sauropods likely evolved voluminous digestive systems. Fermentation chambers, possibly aided by symbiotic microbes, would have broken down fibrous material slowly and thoroughly. There is no evidence yet of chewing mechanisms in these early forms. The teeth were too simple, too undifferentiated. So the entire digestive strategy seems to have been ingest, ferment, extract, and repeat. Chewing was for amateurs. Yet, even as sauropods began embracing their size, they remained surprisingly agile in one crucial way: reproduction. Unlike large, modern mammals that bear live young and invest heavily in few offspring, sauropods laid clutches of eggs. This allowed even giant species to reproduce prolifically. While none of the early sauropods of the Jurassic have left behind definitive nests, later relatives did, and it's likely this reproductive strategy was present from the beginning. For a lineage aspiring to global dominance, high egg output meant resilience. No matter how big they got, they remained at heart reptiles. Still, despite all this innovation, these early sauropods lived in a world that could have shut them down at any moment. The Triassic extinction was still fresh, ecosystems were still unstable. Volcanic eruptions, climate swings, and shifting coastlines all posed risks, and yet these animals persisted, slowly, methodically, eating, walking, and evolving their way into history. What began in the swamps of Africa and the riverbeds of China would soon take over entire continents. But in this moment, between 200 and 180 million years ago, they were still newcomers, still trying things, still awkward, a little lumpy, maybe a little slow, but they were onto something. Something very big, and the planet for once wasn't saying no. There's a moment in deep time when sauropods stop experimenting and start dominating. Between 170 and 155 million years ago, something shifts. The bones get larger, the tails stretch longer, the necks become absurd, and the tracks begin appearing in groups, not scattered footsteps of wandering browsers, but parallel paths moving together. Herds, entire herds of animals longer than a school bus, walking in sync across floodplains and mudflats, their bodies casting kilometre-long shadows at dusk. This is the Middle Jurassic, and this is when sauropods take over the land. Not the titanic forms you might be picturing, not yet. These are still the earlier dynasties, a mix of lineages trying out different evolutionary tricks. In China, a creature called Shunosaurus leaves behind an almost comedic contradiction. It's small for a sauropod, maybe 9 meters long, with a relatively short neck and stout legs. But what draws attention is the tail. At the end of its vertebral taper, where most sauropods narrow off into a whip or bludgeon, Shunosaurus carries a literal club. A mass of bone, spiked, calcified, reinforced. We used to think only ankylosaurs bothered with tail clubs, but this one hit early, and for a while Shunosaurus wasn't alone. In northern Africa, Spinosaurus surfaces from Jurassic layers with equally strange vertebrae. Its spine features elongated neural spines, fin-like projections rising from its back like a row of jagged sails. These aren't just ornaments. They might have anchored strong back muscles, aided in thermoregulation, or served as display, or maybe they were simply there to make predators second-guess the shape of dinner. But the real magic in these Middle Jurassic sauropods isn't just in their anatomy, it's in their context. Because this is the point in history when sauropods stop being isolated curiosities and start being ecosystems. Their fossils appear not just in China and Morocco, but across Europe, in Spain, France, and Germany. Often in groups, often in sediment that speaks of river crossings, shared pathways, synchronized migration. Footprints preserved in the stone of old floodplains show dozens of animals walking the same route, sometimes overlaid, sometimes side by side. And when you track the stride lengths and foot widths, a pattern emerges. Small individuals in the middle, larger ones at the edge, something that suspiciously looks like protection. They were organising, not in the human sense, but in a way that suggests presence. Presence of others, presence of danger, presence of young worth shielding. Why would a creature that size bother travelling in groups? When you're 20 tons and made of muscle and bone, what do you fear? Apparently, enough. The Middle Jurassic wasn't a peaceful chapter in Earth's story. While sauropods were pushing their bodies toward new extremes, predators were evolving in parallel, faster, smarter, more coordinated. Allosaurids were just beginning to appear, and their ancestors, smaller but likely agile and opportunistic, stalked the margins of these herds. A lone juvenile sauropod would have been a walking invitation. In that context, size wasn't always enough. Numbers mattered, and so did timing. Moving as a unit may have been one of the earliest strategies these giants used not to dominate, but to survive. Fossilized bone beds in regions like Xinjiang and the Atlas Mountains often show a mixture of ages and sizes. Some of these assemblages look chaotic, like the aftermath of flash floods, but others have structure. The distribution of remains suggests that these dinosaurs didn't just live in groups, they died in them. Whether caught by rising water or volcanic ash, or the slow sink of a floodplain, they left behind more than bones. They left echoes of a social world we can barely guess at. This surge in diversity, behaviour and form during the Middle Jurassic wasn't limited to one lineage. It was a sauropod renaissance. In England's Oxford clay, remains of Cetiosaurus continue to rewrite our understanding of early titanosauriforms. Once dismissed as a plodding relic, Cetiosaurus now appears as a potential forerunner of later giants. Its bones show signs of rapid growth, internal air sacs, and powerful columnar legs, not unlike what we see later in Brachiosaurus and its cousins. Meanwhile, the air sac system itself, that lightweight, lung-boosting anatomical feature found in birds today, starts showing up in sauropods of this period. It's an elegant solution to an enormous problem: how to keep blood oxygenated and muscles moving across a neck longer than a city bus. Air sacs hollowed out the bones, made the skeleton lighter, and likely allowed a kind of unidirectional breathing, far more efficient than the in-and-out lungs of mammals. We don't have soft tissue, of course, but the bones tell their story. Vertebrae from Patagosaurus, found in Argentina, show the hallmark pitting and internal cavities of pneumatic invasion. This wasn't just bulk, it was biology honed for lightness, reach, and power. And still, the tails kept growing. While Shunnosaurus had its club, others went the opposite direction. Whip-like tails with over 70 vertebrae began to show up across multiple lineages. Some paleontologists suspect they were used as actual weapons, cracking like a sonic boom to deter attackers. Others suggest they were used for balance, display, or intraspecies communication. We don't know. What we do know is that by the time you get to the end of this period, the sauropods weren't just large, they were engineered. They were walking scaffolds of atmospheric strategy, digestive overdrive, and passive defence. They ate low, they ate high, and they likely fermented everything in vast internal vats. Some had peg-like teeth designed for raking ferns and conifers. Others had spoon-shaped mouths, or narrow snouts ideal for precision browsing. Their skulls shrank even as their bodies ballooned, a strange inversion of our own trajectory. Perhaps because brain power wasn't what helped you live to 100 feet long, but none of this, the herds, the tails, the air sacs, the group migrations, was inevitable. These adaptations didn't come with the blueprints. They came with trial and error, and likely extinction. That's the quiet truth behind every dinosaur fossil. It isn't just a winner's story, it's a survivor's compromise. The Middle Jurassic sauropods were bigger, smarter in their own way, and more coordinated than what came before. But they weren't immortal. Most of the forms from this era would vanish before the late Jurassic began, replaced, outcompeted, or simply erased by time. Still, for a brief flicker of geologic time, just 15 million years or so, they ruled the floodplains. They breathed through bones, they fought with tails, and they walked together, vast and slow and humming with a kind of biological ambition we can still barely grasp. So the question remains, what was it about this exact moment, this middle chapter between dawn and dominance, that lets sauropods rewrite the rules of size itself? And why, after all that innovation, did evolution still decide to start over again? Alright, imagine a creature so long that its nose could be sniffing ferns in one clearing, while its tail was still blocking the sunlight in another. Now imagine hundreds of them, moving, breathing, feeding, quiet, living skyscrapers on the march. If earlier sauropods were the proof of concept, what we see in the Morrison Formation is the fully scaled-up prototype. This is the late Jurassic, and in this golden window of time, some of the largest land animals to ever exist walked together across the ancient floodplains of what is now North America. And somehow, they didn't break the planet while doing it. What allowed something like Diplodocus to exist? A creature longer than a commercial airliner, heavier than a convoy of elephants, and still graceful enough to not sink into the mud with every step. The answer isn't a single trait. It's a symphony of anatomical, ecological, and evolutionary improvisation. First, the neck. While earlier sauropods like Shunnosaurus had started extending their vertebrae like cautious engineers testing cantilevers, by the time Diplodocus evolved, nature had gone all in. The cervical vertebrae of Diplodocus were not just long, they were hollowed out, strut-reinforced, and air-sac riddled. That meant lighter bones without sacrificing strength, something like a suspension bridge made of bone. Then there's the gut, a digestive factory longer than most predators. In a world with no grass and no flowering plants, sauropods had to make do with gymnosperms, ferns, and the less than nutrient-dense vegetation of their time. So they became fermentation tanks, long, slow microbial breakdown zones where food stayed for days. Sauropods didn't chew, they swallowed and relied on their size, gut, and possibly gastroliths, stone swallowed for grinding, to extract energy from cellulose-rich plants. Some estimates suggest digestion may have taken weeks, and that's fine when you're big enough that nobody's rushing you. The Morrison Formation, that ribbon of fossil-rich rock stretching from New Mexico to Montana, offers us a frozen moment in this biological arms race. We find Diplodocus here, of course, but also Apatosaurus, Camarasaurus, Barosaurus, and that vertically inclined oddity, Brachiosaurus. Each one reveals a different architectural take on the same problem: how to turn sunlight into mass when you can't photosynthesize yourself. Camarasaurus, for example, was more compact, with stronger teeth, possibly better suited to tougher vegetation. Brachiosaurus, with its giraffe-like posture, may have grazed the canopy while its cousins raked the mid-level foliage. Ecological partitioning allowed giants to share space without competing directly, and the fossil record suggests that multiple sauropod species often coexisted in the same environments. Their bones are scattered in floodplains and streambeds, in places where seasonal rivers once carved through fern prairies. Their footprints, preserved in soft sediment, suggest group movement, not chaotic stampedes, but something that might resemble loose herding. Perhaps females congregated during nesting seasons, or juveniles stayed close to protective adults. There's no fossilized choreography, but the spatial layout of trackways suggests intentionality. They weren't just wandering, they had roots. What about speed? Let's break the illusion. Despite the size, most sauropods were not slow-motion slugs. Computer modelling based on limb proportions and joint articulation suggests walking speeds around 2 to 5 kilometers per hour. Not exactly athletic, but not static either. Their legs were columnar, elephantine, but their stride was efficient. If you were a predator, say a Torvosaurus or Allosaurus, you wouldn't just go after a healthy adult Diplodocus. It wouldn't be a fight, it would be a disaster, and here's where biomechanics gets even stranger. That enormous tail, often depicted dragging behind them like an afterthought, may have been one of their most important tools. We've covered whip theories already, but even without sound barrier snaps, that tail could have served as a visual deterrent or even a balance counterweight for the front-heavy neck. In life, Diplodocus may have carried its tail raised, curving slightly, like a biological boom crane balancing a neck-heavy front. The growth story is no less staggering. Paleohistology, the study of bone microstructure, tells us that these animals grew fast, extremely fast. Diplodocus may have hatched at the size of a large chicken and reached several tons within 2 decades. That kind of metabolic acceleration implies a physiology somewhere between reptilian cold-bloodedness and mammalian warmth. Maybe it's time we stop framing it as a spectrum and accept that dinosaurs were their own category, their own thermal compromise. But size alone doesn't explain survival. The Morrison giants lived in a world of shifting seasons, volcanic episodes, and fluctuating sea levels, and yet for tens of millions of years they persisted, unchallenged in scale, unbothered by rivals, and strangely delicate for their bulk. Their bones are pneumatic, their energy budgets efficient, and their evolutionary pathway precise. These weren't accidents of growth. They were masterclasses in engineering, so could you outrun one? Probably. Could you outlast one? That's trickier. These animals outlived entire biomes. Their herds moved through landscapes that would one day become deserts, cities, oil fields. Diplodocus doesn't care about human time. Its vertebrae once held up 30 meters of neck, not to intimidate, but to reach. And reaching, in the end, may be the whole point. Why else build a creature this long? Shall we find out what hunted them? If you're ready, we'll follow the shadows next. But there's something else in those fossil beds. Something we almost miss in the grandeur of the bones. Bite marks, stress fractures, healed trauma. These were not invulnerable giants gliding peacefully through a prehistoric utopia. Their bones record a rougher truth. We see impact injuries that likely came from intraspecific clashes. Tail strikes, neck blows, perhaps jostling for mates or dominance. Some paleontologists even argue that certain tail fractures show signs of regeneration, which means these giants didn't just live long, they lived long enough to recover. And what of the young? We rarely find juvenile sauropod remains in the same numbers as adults. That could mean many didn't survive their first few years, preyed upon before their size offered protection. Or it could mean they lived in different ecological zones, away from the floodplains where most fossilization occurs. There's a haunting gap in our understanding of their early life stages. Nesting grounds remain elusive. Eggs, when found, are modest, often no larger than a soccer ball. Even giants begin as something you could hold in your arms. Their extinction would come later, long after the Jurassic curtain closed. But for this moment, for these 10 million years, the sauropods of the Morrison ruled an ecosystem that had adapted to accommodate them. Trees evolved higher canopies, riverbanks widened under their feet, even the carnivores got bolder. But none matched their combination of scale, grace, and longevity. So the next time someone calls dinosaurs dumb or lumbering, ask them how many species they know that needed an entire continent just to stretch their legs. Ask them what kind of world is stable enough to grow bones 40 meters long. And ask them if we'll ever build anything that lasts as long as a Diplodocus femur buried in the river mud. Some of the most terrifying creatures in Earth's history never made it into movies. They didn't have the publicist, they came too early, and their bones, when found, rarely include the full picture. But between 190 and 165 million years ago, a different caste of carnivores ruled the Mesozoic stage. Long before the reign of Allosaurus or the rise of Tyrannosaurus, the world was shaped by predators with strange ornamentation, unusual proportions, and evolutionary experiments that mostly didn't survive the final edit. This is the era of the mid-Jurassic meat-eaters, the ones with crests, with strange arms, with group hunting potential, and teeth that looked like nightmares written in enamel. Start with Dilophosaurus. It lived roughly 193 million years ago in what is now Arizona, roaming floodplains under humid, monsoonal skies. For years, it suffered the indignity of Hollywood confusion, miscast as a tiny frilled spitter, when in truth it was nearly 7 meters long, with a sinuous tail and jaws that could easily crush bone. But what truly set Dilophosaurus apart were the twin crests that rose from its skull like arched blades. They were thin, hollow, and likely served no role in combat. Instead, they may have signalled maturity, identity, or status, a biological billboard in a world where eyesight ruled the senses. Despite their elegance, the crests are fragile and almost never fossilise intact. Much of what we know comes from just a few partial skulls, cross-referenced and reconstructed like forensic puzzles. The bones are gracile, but the build wasn't weak. The forelimbs were strong and likely used in grappling or pinning. And while there's still debate over whether it hunted alone or in pairs, new data suggests Dilophosaurus may have targeted prey much larger than itself, using its speed, coordination, and long claws to bring down juvenile sauropodomorphs. Shift to southern Africa, and a slightly younger carnivore steps into view, the ceratosaurs. These were an entirely different lineage, not ancestors of later giants like Allosaurus, but a parallel branch of the theropod tree that diversified early, spread widely, and then quietly faded from dominance. Ceratosaurs have an awkward elegance to them. Their skulls were often deep and ornamented, with ridges or small horns. Their arms, by contrast, were comically small, and some genera even more reduced than in tyrannosaurs. But their legs were built for sprinting. They were lightly built with long tails for balance, and likely used ambush tactics to take down prey across the open fern plains of the mid-Jurassic. The best-known genus, Ceratosaurus, lived slightly later and overlaps with the next wave of Jurassic giants, so we'll save it for the next chapter. But its early relatives, like Elaphrosaurus in Tanzania or Berberosaurus in Morocco, hint at a strange diversity of lightly built predators that once ran through Jurassic floodplains, each experimenting with a different evolutionary strategy. In the forests of China, another story was unfolding. Here, fossil beds preserve not just bones, but delicate impressions of skin, muscle, and sometimes even internal organs. It is in these deposits that we begin to see a more refined version of predator design. Light skeletons, long tails, and occasionally odd features we can't fully explain. For instance, Limosaurus. Technically a ceratosaur, it started life with teeth and lost them as it aged. Adults were toothless, possibly herbivorous, with a beak-like structure instead. Why would a theropod evolve this way? What survival advantage did it offer? We don't yet know. But it suggests a period of intense ecological experimentation during the mid-Jurassic. Not every predator stayed a predator. Not every lineage aimed for size and muscle. Some downsized, specialised, or took evolutionary detours that wouldn't be repeated. And then there's the question of social hunting. Fossil trackways in Zimbabwe and parts of North America from the mid-Jurassic show patterns of multiple theropods moving together, parallel, spaced evenly, travelling in the same direction. Are these the traces of a coordinated hunt, or just parallel travel across a landscape with limited paths? No bones accompany the tracks, so we're left guessing. But if early ceratosaurs or Dilophosaurus relatives did hunt in loose groups, it would mark a significant behavioural shift long before it's seen in their larger descendants. Pack behaviour is notoriously hard to prove in deep time, but trackways, bite mark patterns, and even prey bone distributions can offer subtle clues. And when we step back and look at the mid-Jurassic predator map, a pattern starts to emerge. Lighter frames, faster movement, social possibilities, and an unusual willingness to diversify. This was a time before apex dominance. The world wasn't yet ruled by massive skulls and bone-crushing jaws. Instead, it was shaped by lean predators with specialised senses and niche strategies. Some relied on speed, others on stealth. Some may have used display as much as strength, dazzling rivals with crests or skin colour, the way modern birds of paradise use feathers. And if that comparison feels strange, remember, birds are theropods. And many of the features we now think of as avian were slowly taking shape in their ground-running ancestors. There's an awkwardness to these mid-Jurassic carnivores that's strangely human. They're transitional, they're trying things out. And like many evolutionary experiments, most of them didn't last. But they mattered. They set the stage. They occupied ecological roles during a time of explosive diversification. And they remind us that the age of dinosaurs wasn't just about size, it was about adaptation, in whatever form worked best. So how do we know when evolution is practicing? What does it mean when a lineage branches, fizzles, or disappears entirely? These mid-Jurassic predators leave behind no living descendants, but they leave clues, in jaw design, in bone microstructure, in the shape of a crest no one quite understands, and even in the trackways of animals who might have been walking together, across a mudflat through a forest, towards something none of them could see coming. And as the Jurassic progressed, something else was coming. Larger predators, deeper jaws, teeth built for snapping bones. The age of experimental speed was about to give way to an age of brute force. But before that happened, a different kind of killer ruled the floodplains. Light-footed, sharp-eyed, ornamented, and strange. So the next time someone tells you Jurassic predators were all giant lizards with tiny arms, remember Dilophosaurus, remember the ceratosaurs, and remember that evolution, like science, is never finished, only paused between drafts. And perhaps what makes these mid-Jurassic carnivores so fascinating isn't just what they were, but what they weren't yet. They hadn't settled into the ecological extremes that later predators embodied. They weren't the top-heavy, deep-skulled monsters of the late Jurassic. They weren't yet locked into the apex script. Instead, they were still writing the rules. Their limbs were long, their hands still functional. Their skulls varied wildly, narrow, crested, horned, or bizarrely ornamented. Even their diets might not have been uniform. Some smaller ceratosaurs may have supplemented with scavenging, or even small vertebrates and invertebrates, flexible in ways that future giants couldn't afford to be. We also begin to see something quietly revolutionary: increased sensory specialization. Enlarged olfactory bulbs, forward-facing eyes, and longer cochlear canals, all signs that sight, sound, and smell were becoming central to hunting strategy. The brain cases of some ceratosaurs suggest a neurological investment in balance and coordination, hinting at creatures capable of sudden bursts of motion and finely tuned responses. These weren't dull reptiles reacting on instinct. They were sensory-driven hunters living in complex ecosystems, competing not just with one another, but with crocodilians, early mammals, and each other's cousins across continents still breaking apart. And then there's the open question of vocalization. Did these predators call to one another through the trees? Did crests serve as acoustic resonators as well as visual signals? The fossil record doesn't tell us. But bioacoustic studies in modern birds and reptiles suggest it's possible, and that long before the roar of a lion or the scream of a pterosaur, there may have been deep, eerie sounds echoing across Jurassic floodplains, from hunters no longer remembered. What they left behind was fragmentary, but what they represented was essential. A blueprint of carnivory still in flux, still evolving, and still not quite settled into the shape we think of when we picture a killer. By the late Jurassic, the hunt had changed. The rules weren't written in speed alone, or stealth, or even brute force. It was now a question of scale, not just how large a predator could become, but how large a prey animal it could dismantle. And standing at the top of that evolutionary contest were the undisputed apexes of their time. The broad-skulled, high-spined, meat-shearing theropods who didn't need feathers to dominate. They needed teeth, torque, and time. Allosaurus fragilis, Megalosaurus bucklandiae, and a supporting cast of carnivores now mostly reduced to museum labels, once stalked the floodplains and fern savannas of a world built for giants. And it wasn't just their size that made them remarkable, it was their method. Allosaurus, for instance, wasn't even the largest carnivore in its ecosystem, but it may have been the most efficient. At over 8 meters in length, with a skull built less like a crushing vice and more like a serrated hatchet, it hunted not with the grip of a tyrannosaur, but with the precision of a repetitive striker. Its jaws weren't especially strong when measured against its later relatives, but its neck was something else entirely, muscled, robust, and capable of driving the skull forward in a downward arc. This has led to one of the most widely discussed and still debated models in dinosaur paleobiology, the hatchet attack. Allosaurus may have slammed its head down into prey like an axe, pulling back with jaws already halfway closed, not to crush, but to tear. The biomechanics support it, at least partially. CT scans of Allosaurus skulls show adaptations for impact absorption, with air pockets that would reduce shock and ligaments that could act like biological seatbelts. The jaw joints were loose, able to expand slightly outward, allowing the skull to better grip struggling prey, a feature seen in other predatory theropods, but taken to a more extreme degree here. In short, this was not a bite-and-hold predator. This was a slice-and-retreat specialist, possibly attacking in repeated bursts until the target collapsed. And in a world filled with sauropods the size of apartment buildings, it might have needed every one of those adaptations just to survive the meal. Megalosaurus, despite being the first dinosaur ever scientifically named, remains more of a shadow. Most of what we know is fragmentary, jawbones, femurs, partial vertebrae, and yet the animal casts a long legacy. Unlike Allosaurus, which is now known from dozens of well-preserved specimens, Megalosaurus is a ghost pinned to a name, reconstructed and revised over centuries. But what seems increasingly clear is that it represented a broader, older family of predators, the megalosaurids. These were wide-bodied, heavy-legged hunters with deep skulls and potentially ambush-based strategies, and they filled ecological niches across Europe and beyond. Some reconstructions suggest Megalosaurus may have been a more traditional bite-and-hold predator, clamping onto prey and using its own weight to bring it down. Unlike the repeated strikes of Allosaurus, this might have been a slower but more brutal approach, a locking grip, then a kill by blood loss, collapse, or suffocation. Of course, much of this is theoretical. The fossil record is generous with questions and stingy with answers, but when the ground gives up even a single tooth, we still learn something. About wear patterns, about stress distribution, about the way jaws closed and teeth tore. Paleontology, at its heart, is the study of violence in deep time, and these predators were some of its clearest authors. The environments these giants ruled over were no less dramatic. The Morrison Formation, stretching across what's now the western United States, was a seasonal world of floodplains, braided rivers, cyclical droughts, and fern-dominated undergrowth. It teemed with sauropods, Diplodocus, Apatosaurus, Camarasaurus, and they weren't alone. Juvenile stegosaurs, ornithopods, small scavengers, and crocodilian ancestors all moved through this ecosystem like pieces on a board far too complex to map. And somewhere in the high grasses or low shade, Allosaurus waited, Or maybe it didn't wait at all. There's evidence that it hunted in bursts, possibly in groups. Trackways suggest multiple individuals moving in the same direction with similar spacing, a potential indicator of coordinated hunting. But evidence of true pack behaviour is murkier. Most paleontologists stop short of calling these social animals. They may have hunted in opportunistic gangs like Komodo dragons or hyenas, drawn together not by cooperation but by the smell of blood. And then there's the bone bed evidence. Multiple Allosaurus skeletons found in the same region, sometimes with bite marks, on each other. Was it scavenging, competition, cannibalism? Possibly all three. Apex predators are opportunists first, and saints never. One of the most haunting examples of dinosaur behaviour comes from a Camarasaurus skeleton found with puncture wounds to the cervical vertebrae in the neck, perfectly spaced to match the teeth of an Allosaurus. The wound appears to have healed. That means the attack didn't kill the animal. It survived. For a while. It lived with a torn neck and continued browsing in a forest where death walked on two legs. This fossil, as mundane as it sounds, might be our clearest window into the brutality of Jurassic life. There were no safe zones, only moments between teeth. And it wasn't all brute force. Skull studies of Allosaurus show large olfactory bulbs, suggesting a keen sense of smell, possibly used for long-distance tracking or scavenging. The inner ear structures suggest good balance and head orientation, useful for both ambush and pursuit. In essence, these were not just killing machines, they were sensory organisms in tuned ecosystems. Every step, every movement was shaped by millions of years of evolutionary trial and error, and every successful hunt left its mark, on bone, on ground, on lineage. Today, Allosaurus stands in the halls of natural history museums around the world, jaws open in a permanent snarl, often posed against a rearing herbivore. But the truth is quieter. These were not monsters. They were animals, governed by hunger, instinct and opportunity. The terror they inspired was not personal, it was ecological. They were necessary. The size of the prey had demanded it. So how did these predators kill each other? Slowly, when the blood didn't flow fast enough. Brutally, when opportunity turned to conflict. Or perhaps like falcons, fast, precise, and with a silence that vanished before the next thunder rolled in. We can't be sure. The bones whisper, but they do not sing. And what they whisper is this: the apex was never safe. It was merely next in line. What ruled the skies before birds? The answer isn't just strange, it's astonishing. Because long before any feathered form ever dared to glide, another group had already turned the atmosphere into its hunting ground. They weren't dinosaurs, but they lived alongside them. They weren't birds, but they flew. Their bones were hollow, their wings membraned, and their bodies built for a dimension most Jurassic animals never entered. They were the pterosaurs, and during the Jurassic they didn't just exist, they exploded. The fossil record, sparse but generous in the right places, shows a world slowly filling with winged experimentation. From the lagoons of what is now Germany to the volcanic deposits of northeastern China, these creatures took 1,000 forms. Some, like Rhamphorhynchus, had long tails tipped with diamond-shaped rudders. Others, like Anorognathus, looked like flying frogs with bat wings. And some, like Pterodactylus, dropped the tails altogether, embracing a more streamlined future. All of them were variations on the same ancient gamble, to swap land for sky and claws for clouds. The physics of it shouldn't have worked. Not with reptiles, not with the sheer mass of some of these creatures. And yet they solved the problems. They evolved lightweight pneumatic bones, essentially hollow scaffolds reinforced from within. They grew keeled breastbones to anchor strong flight muscles, developed elongated fourth fingers to support their wing membranes, and evolved structures in their brains that suggest acute spatial awareness. They even show signs of pycnofibers, hair-like filaments that may have helped with insulation, or even rudimentary thermoregulation. In short, they weren't just gliders, they were flyers, in every aerodynamic sense. Rhamphorhynchus, for instance, is one of the best preserved Jurassic pterosaurs, known from dozens of specimens pulled from the Solnhofen limestone in Germany. It had a wingspan of just over 1 metre, a long tail for stability, and forward-pointing teeth that suggest a diet of fish. Its jaws were narrow and curved, perfect for snatching prey from the surface of shallow lagoons. Many specimens have been found with preserved stomach contents, or even the silhouettes of the fish they had eaten. In one case, the fish was still lodged in its throat, a fossilised final meal. But not all pterosaurs were fishing specialists. Some, like a Neurognathus, had broad mouths and short skulls, more suited to catching insects in flight. This was likely an agile, manoeuvrable flyer, with large eyes and strong but compact wings. Its name means tailed frog, though it had more in common with a dragonfly in hunting style. The presence of neurognathids in the Chinese Jurassic beds shows that even by this time, pterosaur evolution had already diversified far beyond a single niche. Pterodactylus, often confused as a generic term for all pterosaurs, was in fact its own distinct genus, one of the first discovered and still one of the most iconic. It lacked the long tail of earlier forms, suggesting a shift toward more bird-like flight mechanics. Its wings were long and narrow, optimized for soaring rather than flapping. This might indicate a shift in lifestyle from active hunting to longer glides over water or open terrain. These creatures may have ridden thermals the way vultures do today, covering large distances with minimal energy expenditure. There is increasing evidence that some pterosaurs nested in colonies, possibly along cliff sides or island coasts. While no Jurassic nests have been definitively confirmed, later specimens from the Cretaceous show clusters of eggs and individuals grouped together, hinting that social behaviours may have had earlier origins. Some species even show signs of sexual dimorphism, differences in crest size or skull shape between males and females, suggesting that display and mating rituals played roles in their behaviour. And then there are the wing membranes. These weren't just skins stretched between fingers. They were complex, multi-layered tissues with muscle fibres, blood vessels and structural stiffeners called actinofibrils. In some species, the wings may have been capable of adjusting stiffness mid-flight, allowing for nuanced control over lift and drag. The trailing edges anchored not to the torso but to the hind limbs, forming a broad flight surface that ran down the sides of the body, a design utterly unlike anything alive today. They were, in many ways, the ultimate alien pilots of the Mesozoic. How did they launch? This has been one of the more surprising revelations of recent studies. Unlike birds, which primarily use their legs to jump and wings to flap upward, many pterosaurs may have used a quadrupedal launch. They vaulted off the ground using both forelimbs and hind limbs, leveraging strong arm muscles to push themselves skyward in a catapult motion. This makes sense when considering the anatomical proportions. Their arms were often far more muscular than their legs, and their centre of gravity placed squarely at the chest. They didn't flap up, they sprang. As for their extinction, well, that story doesn't belong to the Jurassic. These creatures would continue to evolve into monstrous forms in the Cretaceous, some as small as sparrows, others larger than modern aircraft. But their roots are here, in the Jurassic skies, where they first cracked open the boundaries of evolution and dared to inhabit the thin air above it all. Today their bones are rare. Most pterosaur fossils are fragile, crushed and scattered. But when conditions are perfect, an anoxic lagoon, a quick burial, a soft carbonate mud, they preserve like ghosts. Full wings, tooth rows, eye sockets, even, in some miraculous cases, the soft outline of crests or skin. These are the reminders, the aerial shadows. The sky was never empty. It was just waiting for something to rise into it. And before birds, before feathers took their final form, it was the pterosaurs who looked down on the world from above. The first vertebrates to fly, not because they had to, but because evolution, somehow, made it possible. If you stood on the edge of the world 145 million years ago, you might not have noticed anything remarkable. No great bang, no sudden silence. The dinosaurs did not vanish. The skies did not darken. The seas did not retreat. The end of the Jurassic was, in a way, an illusion. Not a catastrophe, but a quiet rearrangement of life's gears. And yet, in the fossil record, the evidence is clear. Something changed. Ecosystems shifted. players swapped roles. The rules of the evolutionary game tilted slightly. But without fire or flood to mark the transition, how do we even define the ending of an era? Geological periods are not decided by sentiment. They are stratigraphic decisions, drawn from boundaries of fossil turnover, isotope ratios, or radiometric spikes in zircon crystals. The boundary between the Jurassic and the Cretaceous is one of the softest transitions in the Phanerozoic. Across North America, Europe and Asia, sediment layers marking the final chapters of the Jurassic blur seamlessly into those of the early Cretaceous. No iridium layer, no shocked quartz, no crater. Just a turnover in flora, a rebalancing in fauna, and a quiet reshuffling of who dominates what niche. What shifted then, if not the planet's crust or the climate's wrath? Some of the most important changes came from below our feet, in root systems, vascular strategies, and the opening experiments of angiosperm evolution. While true flowering plants would not dominate until the Cretaceous matured, their first whispers began here. Small weedy ancestors of the angiosperms, likely evolving in disturbed habitats, began to push into ecological spaces that gymnosperms had held for millions of years. They were not yet trees, they were not yet fruit-bearing. But they were something new, and evolution loves new. The undergrowth wasn't the only arena of change. In the oceans, shifts in plankton species began to alter nutrient cycles. Radiolarians and dinoflagellates started to be joined, and sometimes outcompeted, by calcareous nanoplankton, which would go on to build the chalky deposits that gave the next period its name. This quiet microbial revolution slowly restructured the entire marine food web, from filter feeders to apex hunters. Again, no drama, just a subtle cascade of ecological dominoes. Meanwhile, on land, dinosaur ecosystems began to lose some of their Jurassic signature. The towering sauropods of the Morrison Formation, while still dominant, began to be joined by newer lineages of ornithopods and ceratosaurs that hinted at the shapes of things to come. Stegosaurs, once widespread, began to dwindle. Even the massive allosaurids faced new rivals from emerging megalosaur and tyrannosauroid clades, still small, still underdogs, but undeniably present. What makes the Jurassic's end so peculiar is that it teaches us about continuity, not collapse. The biosphere didn't reset, it reorganized. New patterns began to emerge in old systems. Evolution, never pausing, started painting in a different style. It is one of the rare transitions in Earth's history where the melody didn't stop. It modulated, and yet we only notice it with hindsight. At the time, the creatures living through this change would not have sensed an ending. Only scientists sifting through strata and sorting fossils can now mark that a page quietly turned. In a world addicted to climaxes and catastrophes, the end of the Jurassic offers something strange, a non-ending, a phase shift without a finale. And perhaps that's the real reason it's overlooked. We expect fire, we crave drama, but most of deep time doesn't care what we expect. It just continues, quietly, endlessly, leaf by leaf, tooth by tooth, generation by generation. So the next time you think about endings, remember this: not everything closes with a bang. Some of the most profound changes in Earth's history arrived like a breeze, not a storm. And when the Jurassic finally gave way, it did so with one last breath of cycads and conifers, one last call from a Rhamphorhynchus winging over a lagoon, and then imperceptibly it became something else. Even without catastrophe, the Jurassic had a rhythm, a slow crescendo of continental reshaping, of coastlines stretching and climates shifting. It was a world where the dinosaurs had achieved near total ecological dominance, where mammals had scattered into crevices and margins, and where the forests themselves had subtly begun to whisper of something new. By the very end of the Jurassic, some plants were experimenting with closed carpels and new ways to protect their seeds. These weren't full-fledged flowers yet, not by any means, but the earlier steps toward angiosperms were likely underway, even if the fossil trail only hints at their eventual bloom. What we see is not a mass extinction, but a mass substitution. Insect diversity began to turn, plant strategies began to shift, the ocean floors continued to change, and in the skies, pterosaurs had spread to almost every corner of the Earth, carving niches before birds would one day claim them. But nothing snapped, nothing broke, No layer of iridium, no shocked quartz, no soot blanket or crater. The Jurassic ended like a warm afternoon dissolving into dusk, a transition so gentle it almost escaped our notice, but it was real, it was global, and it was permanent. And so, the curtain fell, not with a bang, but with a turning of the page. The next chapter would bring flowers, new reptiles, mammals with new plans. But for now, in this final hush before the Cretaceous, the Earth stood between eras, still warm, still green, still breathing, as if the world itself was taking a slow inhale, before everything changed again. Thank you, fellow sapiens, for wandering this timeline with me, for drifting into deep time, for slowing down and remembering. If this helped you fall asleep, helped you study, or simply helped you step out of the noise for a while, thank you for being here. If you think more people should know this story, you know what to do. Like, subscribe, share it with the sapiens in your life, and tell me, are you listening before bed, while working, or somewhere in the world I can only imagine? And as always, stay curious, stay calm. I'll see you in the next story.